Hello, and welcome to Space Historians. I'm glad you're here tonight, ready to let your thoughts drift away from the day's noise and into something vast, something calm, something that stretches beyond the edges of imagination. Tonight, we're going to explore a question so simple it sounds like something a child might ask, yet so profound that it touches the very nature of existence itself. How many galaxies are in our universe? It's the kind of question that makes you pause, isn't it? Not because you don't know the answer, but because the act of asking it opens a door to something larger than knowledge. It invites wonder. It asks you to imagine distances your eyes will never see, light that has traveled longer than civilizations have existed, and structures so vast that our entire galaxy, with its 100 billion stars, is just a single point among countless others. Before we begin counting, before we dive into deep space and ancient light, I want you to take a moment to settle in. Find a comfortable position. Let your shoulders drop. Let your breathing slow. The universe has been here for nearly 14 billion years. It will wait for you. There's no rush. There never has been. If you're listening in the dark, maybe you can see a few stars through your window, or perhaps you're imagining them, those faint points of light that have guided travelers and inspired dreamers for all of human history. Every one of those stars belongs to our galaxy, the Milky Way, but beyond them, hidden in the darkness between, lie other galaxies. Hundreds of billions of them, perhaps trillions. Islands of light separated by distances so enormous that even travelling at the speed of light, you would never reach most of them within a human lifetime, or 1,000 human lifetimes. If this kind of cosmic perspective brings you peace, if numbers spoken softly and distances measured in light help quiet your mind before rest, I hope you'll consider subscribing or leaving a like. It helps this small corner of calm reach others who might need it. And for those already here, thank you. You're part of this journey through the stars. So tonight, let's wander together into the deep. We'll move slowly, thoughtfully, following the light backward through time. We'll meet the astronomers who first dared to count the uncountable. We'll see how a single photograph changed everything we thought we knew. And we'll discover that the question itself, how many galaxies are there, might be more beautiful than any answer we could ever find. The universe is waiting. Let's begin. There was a time, not so long ago, when the universe fit inside a single thought. The Milky Way, that luminous band stretching across the night sky, was everything. Every star you could see, every faint smudge of light, every glowing cloud, all of it belonged to one grand structure. Our galaxy was the universe, and the universe was our galaxy. Beyond it, astronomers believed, lay only darkness, empty space, nothing more. It made sense, in a way. The human eye can only see so far. Even with early telescopes, the view remained limited. The fuzzy patches scattered among the stars, what astronomers called spiral nebulae, seemed like small formations within our cosmic home. Perhaps they were clouds of gas where new stars were being born. Perhaps they were something else. But they were ours, contained within the Milky Way's embrace. Then, in the early decades of the 20th century, something impossible happened. An astronomer pointed a telescope toward one of those spiral nebulae and measured its distance. What he found didn't just expand our understanding, it shattered it completely. That single nebula, the one we now call Andromeda, wasn't inside our galaxy at all. It was far beyond it, unimaginably far, so far that the light reaching Earth had been travelling for over 2 million years. That discovery changed everything. Overnight, the universe expanded from one galaxy to many. The Milky Way lost its claim to being the whole of creation. It became, instead, one island among countless others, adrift in an ocean of space far deeper and darker than anyone had imagined. The number one became two, then dozens, then thousands, then millions, and the counting has never stopped. Every improvement in our instruments reveals more galaxies hiding in the darkness. Every deeper look into space shows us that what seemed empty was actually full. The universe, it turns out, is overflowing with galaxies, each one a collection of billions of stars, scattered across distances that make the mind falter. When you think about it now, it sounds almost obvious. Of course there are other galaxies. Of course the universe is vast. But for most of human history, that wasn't obvious at all. It took centuries of looking, questioning, and measuring before we could even begin to grasp the scale of what surrounds us. Imagine what it must have felt like to be one of those early astronomers, peering through a telescope night after night, sketching the shapes of faint nebulae by hand, wondering what they were. Some appeared as perfect spirals, graceful arms curving outward from a bright centre. Others looked like smooth ellipses, glowing softly without structure. A few were irregular, chaotic, refusing to fit any pattern. They were beautiful, mysterious, and utterly puzzling. For years, the debate raged. Were these nebulae nearby clouds within our galaxy, or were they distant systems far beyond it? The question seemed impossible to answer. Distance, after all, is not something you can measure easily when your subject is millions of light years away. You can't stretch a ruler across space. You can't travel there and back. All you have is light, faint and fragile, arriving after journeys so long that the objects you're seeing no longer exist in the form you observe them. But light, it turned out, was enough. Light carries information. It holds clues about where it came from, how far it travelled, and what happened along the way. The trick was learning how to read those clues, how to decode the messages hidden in wavelengths and brightness. When astronomers finally cracked that code, the universe opened like a book. The moment of revelation came not with a shout, but with a careful measurement. A single star, pulsing rhythmically inside the Andromeda Nebula, gave away the secret. Its brightness changed in a predictable pattern, and that pattern revealed its true luminosity. By comparing how bright it appeared from Earth to how bright it actually was, astronomers could calculate its distance. The number was staggering. Andromeda wasn't a cloud within the Milky Way. It was an entire galaxy, separate and distinct, containing as many stars as our own. That realization echoed through the scientific community like a bell. If Andromeda was a galaxy, then so were the others. Every spiral nebula, every faint smudge, every mysterious glow was an island universe of its own. The sky wasn't a single structure dotted with stars. It was a vast expanse filled with galaxies, each one a universe unto itself. The impossible had become real. The universe had grown, not by adding more space, but by revealing what had always been there, hidden in plain sight. The stars we saw were only the nearest layer of a much deeper reality. Beyond them, stretching in every direction, lay billions of galaxies, their light just beginning to reach us after journeys lasting billions of years. And so the question formed, quiet but persistent, like a whisper in the dark. If there are other galaxies, how many are there? Is there a number we can attach to this vastness? Or does it go on forever, layer upon layer, an infinity of light? The astronomers who first asked that question couldn't have known where it would lead. They couldn't have imagined the telescopes we would build, the images we would capture, or the numbers we would eventually arrive at. They simply looked up, measured what they could, and followed the evidence wherever it led. What they found was a universe that refuses to be small. Every time we think we've reached the edge of counting, the edge moves further away. Every deeper look reveals more galaxies than we expected, fainter and more distant, filling every patch of sky. The darkness we once thought was empty turned out to be full of light, just light too faint for our eyes to catch without help. That's the impossible beginning. Not that galaxies exist, but that they exist in such overwhelming abundance. It created an uncountable multitude, scattered across space like grains of sand on an infinite beach. And we, standing on one small planet in one ordinary galaxy, have only just begun to grasp how many there might be. The story of counting galaxies is the story of humanity learning to see. It's about pushing the boundaries of perception, about building tools that extend our senses into the dark. It's about following light backward through time, catching photons that left their sources before life existed on Earth, before the sun ignited, before the solar system formed. Every galaxy we count is a message from the past. Every number we add to the total is a step deeper into understanding. And the question that started it all, the question that seemed so simple, how many galaxies are there, has become one of the most profound mysteries we've ever pursued. Because the answer, it turns out, isn't just a number. It's a revelation. It's a reminder that the universe is larger, older, and more generous with its wonders than we ever dared to imagine. The impossible became possible the moment we looked closely enough to see it, and once we saw it, we could never unsee it again. The universe had shown us its true face, and it was filled with galaxies, more than we could count, more than we might ever count, stretching endlessly into the dark. Angeles, where the air grows thin and the lights of civilization fade into distance, there sits an observatory. Mount Wilson Observatory, perched at an elevation of nearly 6,000 feet, was once the edge of human vision. In the early decades of the 20th century, it housed the most powerful telescope on Earth, a giant instrument with a mirror 100 inches across, capable of gathering more light than any device before it. This was where the universe changed, not all at once, but gradually, through nights of patient observation, careful measurement, and quiet revelation. The year was 1923, though the work leading up to that moment had taken years, and the man at the centre of it was named Edwin Hubble. Hubble wasn't the first to wonder about the spiral nebulae, those faint, ghostly shapes scattered across the sky. Astronomers had been sketching them for decades, arguing about what they were, trying to understand their nature. But Hubble was the one who finally answered the question, not through speculation, but through evidence. He pointed the great telescope toward Andromeda, the brightest of the spiral nebulae, and looked deeper than anyone had before. Night after night, he captured photographic plates, long exposures that allowed the faint light to accumulate slowly over hours. Photography was still a relatively new tool in astronomy, but it had one enormous advantage over the human eye. It could see things too dim for human vision, and it could hold those images still, preserving them for study. Where the eye would blink and lose the faint glow, the photograph would wait, patient and faithful. Among the countless stars in Andromeda, he identified a few that behaved strangely. They weren't constant. Their brightness pulsed, dimming and brightening in a regular rhythm. These were Cepheid variable stars, and astronomers already knew something remarkable about them. The speed of their pulsation was directly related to their true brightness. A fast-pulsing Cepheid was dimmer. A slow-pulsing one was brighter. It was a cosmic ruler, a way to measure distances across space. By observing how fast the Cepheids in Andromeda pulsed, Hubble could calculate how bright they truly were. Then, by comparing that true brightness to how bright they appeared from Earth, he could determine how far away they must be. The math was simple. The result was staggering. Andromeda wasn't close. It wasn't even within our galaxy. It was over 2 million light-years away, far beyond the boundaries of the Milky Way. That single measurement, made in a quiet observatory on a mountain in California, expanded the known universe by an almost unimaginable factor. If Andromeda was that far away, then it couldn't be a small cloud of gas within our galaxy. It had to be something much larger, something comparable to the Milky Way itself. It was, in fact, an entire galaxy, a separate island, of stars drifting in the void. The setting for this discovery was humble. No grand ceremony, no announcement to the world, just one man, a telescope, and a series of careful observations recorded on glass plates. The telescope itself was a marvel of engineering. Its massive mirror ground and polished by hand, mounted in a dome that could rotate to track the sky. The nights were cold at that altitude, and the work was tedious. Hours spent adjusting the telescope, guiding it manually to keep the target in view, waiting for the exposure to complete. Then developing the plates, examining them under magnification, marking each star, comparing images taken weeks or months apart. It was slow work, the kind that required patience and persistence. Hubble wasn't looking for glory. He was looking for answers. And the answers came one photon at a time, building into an image that would redefine reality itself. The mountain where this happened was quiet, far from the noise of the city below. On clear nights, the stars shone with a brilliance rarely seen at lower elevations. The air was steady, free from the turbulence that blurs images through ground-based telescopes. It was the perfect place to see deeply, to catch the faint light of distant objects. The astronomers who worked there lived in small cottages on the mountain, isolated but connected by their shared purpose. They were explorers, but their territory wasn't geographic. It was cosmic. Hubble himself was a careful, methodical observer. He didn't rush to conclusions. He gathered data, checked his measurements, repeated his observations. When he finally published his findings, the evidence was undeniable. Andromeda was not part of our galaxy. It was its own galaxy, and if Andromeda was a galaxy, then so were all the other spiral nebulae. The universe was not one structure, but many, separated by distances that light itself took millions of years to cross. The setting of this discovery matters because it reminds us that great revelations often come from quiet places. There was no particle accelerator, no space probe, no supercomputer, just a mountain, a telescope, and a mind willing to follow the evidence wherever it led. The tools were simple by modern standards, but they were enough. The universe doesn't require elaborate machinery to reveal its secrets. It only requires attention. Mount Wilson became a pilgrimage site for astronomers. Others came to use the telescope to peer into the depths of space, to add their own observations to the growing catalogue of galaxies. The mountain had become a window, a place where the barrier between Earth and the cosmos seemed thinner, where the light of distant galaxies could be captured and studied. The work that began there in the 1920s set the stage for everything that followed. Hubble's measurement of Andromeda's distance was just the beginning. Other astronomers used the same techniques to measure distances to other galaxies, building a map of the universe that grew larger with each observation. The Milky Way, once thought to be everything, became just one point on that map, no more special than any other. The setting also tells us something about the human side of discovery. Hubble wasn't working alone. He relied on assistants who helped operate the telescope, on mathematicians who checked his calculations, on the generations of astronomers before him who had catalogued the nebulae and wondered about their nature. Science is a collective effort built on the work of many minds, each contributing a piece to the larger puzzle. And there was something poetic about the location itself. A mountain rising above the ordinary world, a place where the air was clear and the view unobstructed. It's a fitting metaphor for what astronomy does. It lifts us above the immediate, the local, the everyday, and shows us a perspective that stretches across space and time. From that mountain, Hubble could see what no one had seen before. Not because his eyes were sharper, but because he was looking in the right way, with the right tools, at the right time. The setting reminds us that discovery happens when preparation meets opportunity. Hubble had the telescope, the technique, and the patience. The universe provided the light, travelling for millions of years to arrive at that exact moment, captured on a photographic plate on a mountain in California. It was a meeting of human ingenuity and cosmic timing, and it changed everything. Mount Wilson is still there, though newer telescopes have long since surpassed it in power. But the work that happened there in the early 20th century remains foundational. It was the place where we learned that the universe is filled with galaxies, where we took the first real steps toward counting them. The mountain witnessed the moment when our view of existence expanded beyond measure, when the impossible became undeniable. That's where it all began, on a quiet mountain, under a dark sky, with a patient astronomer and a powerful telescope. The universe revealed itself, one Cepheid variable at a time, one measurement at a time, one galaxy at a time. And we, standing on that mountain in imagination, can feel the weight of that moment. The universe grew, and so did we. The photograph didn't look like much at first. A small glass plate, perhaps 8 inches across, covered with tiny black dots against a greyish background. Each dot was a star, or what appeared to be a star, captured during a long exposure through the world's largest telescope. The image showed a section of the Andromeda Nebula, that distinctive spiral shape that had puzzled astronomers for generations. Edwin Hubble held the plate up to the light, examining it carefully through a magnifying lens. He was looking for something specific, something that would either confirm his suspicions or send him back to the drawing board. What he found that day would ignite a spark that would never be extinguished. A mystery that would lead to more mysteries, expanding outward like ripples on a still pond. Among the countless dots on that plate, one behaved differently. Its brightness had changed since the last time he photographed the same region. That meant it wasn't an ordinary star, at least not in the way most stars appear to us. It was a variable, a star whose light pulsed in a rhythm, dimming and brightening over a predictable period. More observations confirmed it. The star followed a pattern, and that pattern was the key. Variable stars weren't new to astronomy. They'd been observed for years, their rhythmic changes carefully catalogued, but a particular type, the Cepheid variables, had recently been understood in a new way. An astronomer named Henrietta Leavitt had discovered something remarkable about them. She found that the period of their pulsation, how long it took them to complete one cycle from bright to dim and back again, was directly related to their true luminosity. The longer the period, the brighter the star actually was. This relationship was revolutionary because it provided a cosmic measuring stick. If you could observe a Cepheid variable and measure its period, you could calculate how bright it truly was. Then, by comparing that true brightness to how bright it appeared from Earth, you could determine how far away it must be. The dimmer it appeared, the farther away it had to be. Simple geometry, The intensity of light diminishes with distance in a predictable way, following the inverse square law. Double the distance, and the light becomes 4 times dimmer. Hubble had found a Cepheid in Andromeda, and when he calculated its distance using Leavitt's relationship, the number was almost unbelievable. The star, and therefore the nebula it belonged to, was nearly 1 million light-years away. Later refinements would push that distance even farther, over 2 million light-years, but even the first estimate was enough. It was too far too far to be inside the Milky Way. The implications settled over Hubble like a weight. If Andromeda was that distant, then it couldn't be a small cloud of gas or a cluster of stars within our galaxy. It had to be something else entirely. It had to be a galaxy itself, comparable in size to our own, containing billions of stars. The light reaching Earth from Andromeda had been travelling for over 2 million years. When that light began its journey, early humans were just beginning to walk upright on the plains of Africa. The light had crossed an ocean of space, arrived here, and was now being measured by a man standing on a mountain. The discovery was quiet. There was no sudden revelation, no moment of shouting Eureka into the night. Just a careful astronomer, making notes, checking calculations, and realizing that the universe had just become unimaginably larger. Andromeda wasn't alone either. If it was a galaxy, then the other spiral nebulae scattered across the sky were likely galaxies too. Each one a separate island of stars, each one separated from the others by distances so vast that light itself took millions of years to travel between them. The spark of mystery that Hubble ignited wasn't about Andromeda itself. It was about what Andromeda represented. If there were other galaxies, how many were there? Were they scattered randomly through space? Or did they follow some pattern? How far away were the farthest ones? Could we even see them all? Or were some so distant that their light hadn't reached us yet? The mystery deepened with every new observation. Other astronomers began measuring distances to other nebulae, finding that they too were galaxies far beyond the Milky Way. Some were relatively close, just a few million light-years away. Others were much farther, tens of millions of light-years distant. The universe wasn't just larger than we thought, it was larger than we could easily comprehend. And there was something else, something even stranger. When astronomers analyzed the light from these distant galaxies, they noticed a pattern. The light was shifted toward the red end of the spectrum, a phenomenon known as redshift. The farther away a galaxy was, the more its light was redshifted. This wasn't just a curiosity, it was evidence of something profound. The galaxies weren't sitting still in space. They were moving away from us, and the farther away they were, the faster they seemed to be receding. This discovery would later lead to the understanding that the universe itself is expanding, that space is stretching, carrying galaxies apart like dots on an inflating balloon. But in those early days, it was simply part of the mystery. The universe was bigger than expected, and it was also dynamic, not static. Everything was moving, changing, evolving on timescales too vast for human experience but visible to patient observation. The spark Hubble ignited grew into a fire. Astronomers around the world began pointing their telescopes toward the spiral nebulae, measuring distances, cataloguing positions, trying to make sense of the new cosmos that was revealing itself. The Milky Way, once the entire universe, was now just one galaxy among many. And the question that naturally followed was, how many? How many galaxies exist? Is there a limit, or does it go on forever? The discovery also changed how we think about our place in the universe. Before Hubble's measurement, it was still possible to believe that we occupied a special position, that our galaxy was the center of everything. But if Andromeda was a galaxy like ours, then there was no center. Every galaxy was just one among countless others. We weren't at the middle of creation. We were simply part of it, drifting through space like every other collection of stars. This realization carried a strange mix of humility and wonder. Humility because it showed how small we are, how insignificant our position might seem in the grand scale of things. But wonder too, because it revealed how much more there is to explore, how much richness and complexity the universe contains. The discovery didn't diminish us. In some ways, it elevated us. We were part of something vast, something filled with beauty and mystery, something that invited endless exploration. The spark of mystery that began with one Cepheid variable in Andromeda became a quest that continues to this day. Every new telescope built, every deeper survey conducted, adds to our understanding of how many galaxies exist and where they are. The mystery hasn't been solved. It's been expanded. Each answer leads to new questions. Each discovery reveals something unexpected. And perhaps that's the nature of true mystery. It doesn't disappear when you learn more about it. It deepens. The more you see, the more you realize there is to see. The universe isn't a puzzle with a finite number of pieces. It's an infinite canvas, always offering another layer, another detail, another wonder waiting to be noticed. Hubble's discovery lit that spark. One measurement, one calculation, one realization that changed everything. The universe grew in that moment, not physically, but in our awareness of it, and it has never stopped growing since. The news didn't spread instantly. There was no internet, no instant communication across continents. Scientific papers moved slowly, published in journals that were mailed to universities and observatories around the world. When Hubble's findings finally reached the broader astronomical community, the response was mixed, a blend of excitement and skepticism, awe and disbelief. Some astronomers had suspected the truth for years. They had looked at the spiral nebulae and sensed that these objects were too large, too structured to be simple clouds within our galaxy. They had argued in conferences and papers that these might be island universes, separate galaxies like our own. For them, Hubble's measurement was confirmation, vindication of what they had already believed. The universe they had imagined was real, but others resisted. Change comes hard, even in science. The idea that the Milky Way was the entire universe had been comfortable, manageable. It fit within the scope of human imagination. To accept that there were other galaxies meant accepting that the universe was almost incomprehensibly larger than previously thought. It meant reimagining everything, redrawing every map, recalculating every assumption. Some astronomers questioned Hubble's methods. Were the Cepheid variables he found really reliable? Could the distance calculations be trusted? Was there some error in the analysis? The debate that followed was vigorous but ultimately brief. Hubble had done his work carefully. Other astronomers repeated his observations, found more Cepheids in Andromeda and other nebulae, and confirmed his results. The evidence accumulated quickly. Within a few years, the astronomical community had largely accepted the new reality. The spiral nebulae were galaxies. The universe was vast beyond previous comprehension, and humanity's place in it had shifted once again. But beyond the scientific community, the news filtered out slowly to the wider world. Newspapers occasionally reported on the discoveries, though often with confusion or oversimplification. The public, for the most part, continued with their daily lives, unaware that the universe had just expanded exponentially in the minds of a small group of people with telescopes. Yet for those who did grasp the implications, the response was profound. There was awe, the kind that makes you stop and simply stare, unable to find words adequate to the moment. The realization that every faint smudge of light in the telescope might be an entire galaxy containing billions of stars, each potentially with its own planets, was overwhelming. How could something so vast exist? How could we have missed it for so long? Some felt a kind of vertigo, as if the ground had shifted beneath them. The universe they thought they knew had disappeared, replaced by something far stranger and more magnificent. It was like discovering that what you thought was a small room was actually an endless cathedral, its walls extending infinitely in all directions. The sense of scale was dizzying. There was also a deep sense of wonder, the recognition that the universe was more generous with its creations than anyone had dared imagine. It hadn't made one galaxy and stopped. It had made countless galaxies, each one unique, each one a separate cosmos of its own. The abundance was almost incomprehensible. Why so many? What was the purpose of such vastness? The questions didn't have easy answers, but they invited a kind of contemplation that was almost spiritual. For some, the discovery brought a feeling of loneliness. If the universe was so large, and if our galaxy was just one among billions, then perhaps we were truly alone. The distances between galaxies were so vast that even light took millions of years to cross them. If there were other civilizations out there, other beings looking up at their own night skies, would we ever know? Would we ever be able to reach them, or they us? The space between galaxies wasn't just distance, it was time, unimaginable stretches of time that might forever separate one island of consciousness from another. But others found comfort in the discovery. The universe wasn't empty, it was full, brimming with structure and light. Every direction you looked revealed more galaxies, more stars, more possibilities. If life had emerged here, on this one small planet, in this one ordinary galaxy, then surely it had emerged elsewhere too. The sheer number of galaxies, each containing billions of stars, suggested that we were not unique. Somewhere out there, perhaps in one of those distant spirals, other beings might be experiencing the same sense of awe at the scale of existence. The response among scientists was also deeply personal. Many of them had spent years studying the nebulae, sketching their shapes, trying to understand their nature. To learn that these objects were entire galaxies was both humbling and exhilarating. Humbling because it showed how limited their previous understanding had been. Exhilarating because it opened up an entirely new field of study. Suddenly, there was so much more to explore, so many more questions to ask. Some astronomers immediately began planning new observations. If these nebulae were galaxies, then studying them could reveal how galaxies form, how they evolve, how they move through space. The universe became a laboratory on the grandest scale imaginable. Every galaxy was an experiment in structure and time, a test of the laws of physics played out over billions of years. The emotional response extended beyond the immediate scientific implications. There was something profound about realizing that the universe didn't care about human scales or human time. It operated on its own terms, indifferent to our presence. The galaxies had been there all along, shining their light into space. Whether we saw them or not, they would continue long after humanity was gone. That indifference wasn't cruel. It was simply the nature of things, and there was a strange peace in accepting it. For the philosophers and poets who paid attention to these discoveries, the response was rich with meaning. The expansion of the known universe became a metaphor for the expansion of human understanding. We were creatures capable of reaching beyond ourselves, of comprehending things far larger than our immediate experience. The discovery of other galaxies was proof that the human mind, despite its limitations, could grasp the infinite, or at least gesture toward it. Some saw religious significance in the discovery. If God or the universe or whatever name you gave to the creative force behind existence had made so many galaxies, then creation was far more generous and abundant than any scripture had described. The cosmos became a testament to infinite creativity, endless variation, boundless possibility. For those with faith, it deepened rather than diminished their sense of the sacred. Others found the discovery unsettling in a different way. The universe they had known, small and comprehensible, had been replaced by something that defied easy understanding. How do you hold billions of galaxies in your mind? How do you make peace with scales of distance and time that render human life almost meaningless by comparison? The psychological adjustment took time. It required a new way of thinking about existence, one that could accommodate vastness without losing sight of the immediate, the personal, the small moments that make up a life. But perhaps the most common response, the one that united scientists and laypeople alike, was simple amazement. The universe had revealed itself to be far more interesting than expected. The discovery of other galaxies was like opening a door you didn't know was there and finding an entirely new world on the other side. And the best part was that the door was still open. There was more to see, more to learn, more to wonder at. The first response to the discovery was human in all its complexity. Awe, disbelief, excitement, fear, wonder, loneliness, connection. All of these feelings coexisted, sometimes in the same person, sometimes shifting from moment to moment. The universe had grown, and we were still catching up, still trying to understand what it meant. And in the quiet moments, when the debate settled and the calculations were done, there was simply the image of those distant galaxies hanging in space, their light reaching across millions of years to touch us. That image stayed with people. It changed them. Once you knew that the universe was filled with galaxies, you could never look at the night sky the same way again. The darkness became deeper, the light became more precious, and the question of how many galaxies there might be became not just a scientific puzzle, but a meditation on existence itself. There's a strange tension at the heart of astronomy, one that becomes apparent the moment you try to count something as vast as galaxies. On one hand, science demands precision, measurement, verifiable evidence. On the other hand, the universe presents mysteries that resist simple answers, phenomena that push the boundaries of what can be known. Counting galaxies sits exactly at that intersection, where the measurable meets the infinite, where data confronts wonder. The contradiction reveals itself immediately when you ask the question, how can we count what we cannot touch? Galaxies aren't objects you can hold or examine directly. They're patterns of light, photons that have traveled unimaginable distances to reach our instruments. When we say we've counted a galaxy, what we really mean is that we've detected enough light to infer the presence of a massive structure far away. We're counting ghosts, in a sense, echoes of things that might no longer exist in the form we're seeing them. The light from distant galaxies takes so long to reach us that we're always looking into the past. A galaxy 10 million light-years away appears as it was 10 million years ago. A galaxy a billion light-years away shows itself as it existed a billion years in the past. The farther we look, the further back in time we see. So, when we count galaxies, we're not counting the present. We're counting history, layered and complex, each galaxy existing in a different moment of cosmic time. This creates a fundamental problem. The number of galaxies we can see depends on how far we can look, and how far we can look depends on the sensitivity of our instruments. A better telescope reveals more galaxies, not because new ones suddenly appeared, but because we've pushed our vision deeper into space and time. The count is always provisional, always incomplete. There are galaxies beyond our reach. There, light not yet arrived or too faint to detect. The true number remains hidden behind the horizon of observation. Science tries to work around this limitation through statistical methods. Astronomers take deep images of small patches of sky, count every galaxy they can find in those patches, then extrapolate to estimate the total number across the entire sky. It's sound methodology, but it rests on assumptions. It assumes that the small patch is representative of the whole, that the distribution of galaxies is relatively uniform across space. Those assumptions are probably correct, but probably isn't the same as certainly. The contradiction deepens when you consider the nature of light itself. Light is both a particle and a wave, a quantum entity that behaves in ways that defy classical intuition. The photons we catch from distant galaxies have interacted with space itself during their journey, stretched by cosmic expansion, bent by gravitational fields, scattered by dust. By the time they reach our detectors, they carry information, yes, but also noise, distortion, ambiguity. Interpreting that light requires sophisticated analysis, separating signal from background, distinguishing a faint galaxy from instrumental artifacts or cosmic rays. There's also the problem of invisible matter. The galaxies we can see, the bright collections of stars and gas, are only part of the picture. Most of the mass in the universe is dark matter, which doesn't emit light at all. It shapes the distribution of visible galaxies, pulling them into clusters and filaments through gravity alone. When we count galaxies, are we counting only the visible ones, or should we include the dark ones, the halos of invisible matter that might contain little or no starlight? The answer depends on how you define a galaxy, and that definition isn't as clear as it might seem. Then there's the question of what counts as separate. When two galaxies collide and merge, do they become one galaxy or remain two? During the billions of years that collision takes, at what point does the count change? The universe doesn't mark clear boundaries. Galaxies are fuzzy at their edges, blending into the intergalactic medium. Small satellite galaxies orbit larger ones. Where does one end and another begin? The categories we use, spiral, elliptical, irregular, are human inventions imposed on a continuum of forms. Science provides tools to navigate these contradictions, but it doesn't eliminate them. Every measurement comes with uncertainty, every extrapolation with caveats. The number of galaxies astronomers cite, currently around 2 trillion in the observable universe, is an estimate based on the best available data. But it's not a final answer. Future telescopes might reveal that the number is higher, that faint dwarf galaxies outnumber bright ones by even more than we thought. Or they might show that some objects we counted as separate galaxies are actually parts of larger structures. The count will change. The uncertainty will remain. Yet this uncertainty isn't a failure of science. It's a feature of studying something as vast as the cosmos. The universe doesn't owe us simplicity. It doesn't arrange itself for easy counting. The contradictions we face, the gaps between what we can measure and what exists, are reminders that reality is always richer than our descriptions of it. Science gives us a way to approach that reality, to chip away at the unknown, but it doesn't promise to eliminate mystery entirely. There's a strange beauty in this contradiction. The same methods that allow us to count galaxies also show us the limits of counting. The precision of measurement reveals the imprecision of knowledge. We can say with confidence that there are hundreds of billions of galaxies, perhaps trillions. We can map their distribution, study their properties, trace their evolution over cosmic time. And yet, in the same breath, we must admit that the true total eludes us, hidden beyond the reach of light, beyond the resolution of our instruments, beyond the horizon of the observable universe. Mystery, in this sense, isn't the opposite of science. It's its companion. Every answer opens new questions. Every deeper look reveals structures we didn't expect. The Hubble Deep Field showed thousands of galaxies in a patch of sky that looked empty. The James Webb Space Telescope is now finding galaxies even farther away, brighter and more massive than our models predicted. Each discovery adjusts the count, but also reminds us how much remains unseen. This contradiction also touches something philosophical. When we ask how many galaxies exist, are we asking about the observable universe or the universe as a whole? The observable universe is finite, bounded by the distance light has travelled since the Big Bang. Beyond that lies a region we can never see. Regions whose light will never reach us because the expansion of space is carrying them away faster than light can travel. Toward us. Do those galaxies count? They exist, presumably, following the same laws of physics. But if we can never detect them, never verify their presence, do they belong in the total? Science typically limits itself to the observable, to what can be measured and tested. But the human imagination doesn't stop at that boundary. We can conceive of an infinite universe, stretching endlessly beyond the horizon. In such a universe, the number of galaxies would be infinite, rendering the question of counting meaningless. The contradiction then becomes not just practical but existential. The finite meets the infinite. The known brushes against the unknowable. And yet, we keep counting. Not because we expect to reach a final number, but because the act of counting brings us closer to understanding. Each galaxy we catalogue adds to our knowledge of cosmic structure. Each distance measurement refines our models of expansion. Each spectrum analysed reveals details about the composition and motion of distant matter. The process of counting, even when it can't be completed, teaches us about the universe and about the nature of knowledge itself. Perhaps the contradiction resolves not in an answer but in an acceptance. Science and mystery coexist. Measurement and wonder are not enemies but partners in the quest for understanding. The galaxies, countable and uncountable, measurable and mysterious, fill the universe, whether we comprehend them fully or not. Our task isn't to eliminate the mystery but to engage with it, to push the boundaries of what can be known while honouring the vastness of what cannot. The contradiction reminds us that the universe is patient. It doesn't hurry to reveal itself. It allows us to approach slowly, one observation at a time, building understanding gradually across generations. The count of galaxies today is larger than yesterday's. Tomorrow's will be larger still, and the mystery, rather than diminishing, deepens with each new layer of discovery. Science versus mystery isn't a conflict to be won. It's a dance, a balance, a conversation between the human desire to know and the universe's infinite capacity to surprise. Once the reality of other galaxies became undeniable, the question naturally followed, how many are there? But answering that question required more than just pointing telescopes at the sky. It required theory, models, assumptions about the nature of the universe itself. And on those questions, minds divided. Different astronomers, looking at the same evidence, came to different conclusions about the scope and scale of cosmic structure. In the early days, the estimates were modest, almost cautious. Perhaps a few million galaxies, some suggested. After all, even with the largest telescopes of the time, only a limited number of galaxies could be clearly resolved and studied. The assumption, rarely stated but often implied, was that what we could see represented a significant fraction of what existed. The universe might be larger than the Milky Way alone, but it still had boundaries, still fit within comprehension. Others pushed for larger numbers. They argued that the galaxies we could see were only the brightest, the closest. Beyond them, hidden by distance and faintness, must lie countless others. These astronomers pointed to the fact that every improvement in telescopic power revealed more galaxies than before. It suggested a pattern, a pyramid where bright galaxies were rare at the top, but faint ones became increasingly common as you moved down the scale. If that pattern held across the entire universe, the total number could be enormous. The debate wasn't just about counting. It was about cosmology itself, about the fundamental nature of the universe. Was space infinite, stretching forever in all directions? Or was it finite, curved back on itself in some higher dimension? If infinite, then the number of galaxies would also be infinite, making the question of counting meaningless. If finite, there would be a definite total, even if impossibly large. The theories divided along these lines, each camp marshalling evidence and logic to support their view. Some astronomers favored what was called the static universe model. In this view, the universe had always existed in roughly its current form. Galaxies were scattered through space, perhaps moving slightly, but not expanding or contracting as a whole. If this model were correct, then counting galaxies was simply a matter of surveying space thoroughly enough. The number might be large, but it was fixed, unchanging. But Edwin Hubble's observations complicated this picture. When he studied the light from distant galaxies, he found that nearly all of them showed redshift. Their light stretched toward longer wavelengths. The farther away a galaxy was, the greater its redshift. The simplest explanation was motion. The galaxies were moving away from us, and the more distant ones were receding faster. This suggested something radical, that the universe itself was expanding. That space was stretching, carrying galaxies apart like raisins in a rising loaf of bread. If the universe was expanding, then counting galaxies became even more complex. The number we could observe depended not just on distance, but on time. Looking far enough back, we would see the universe when it was younger, denser, perhaps with fewer galaxies or galaxies in different stages of formation. The count wasn't a simple snapshot. It was a composite of different eras, layered on top of each other by the finite speed of light. The expansion also raised questions about the future and the past. If the universe was expanding now, then in the past it must have been smaller, denser, hotter. Wind the clock back far enough, and you arrive at a moment when everything was compressed into an infinitely small point. This was the beginning of what would later be called the Big Bang Theory, though that name came later, coined by a skeptic as a dismissive joke. The theory suggested that the universe had a finite age, roughly 10 to 15 billion years, later refined to about 13.8 billion. Not everyone accepted this. Some astronomers proposed alternative models. The steady-state theory, popular in the mid-20th century, argued that the universe was eternal and unchanging on large scales. Yes, galaxies moved apart, but new matter was constantly being created in the spaces between them, forming new galaxies to replace the ones that moved away. In this view, the number of galaxies in any given volume of space remained constant over time. The count would be large, but stable. The theories divided not just on numbers, but on philosophy. The Big Bang implied a beginning, a moment of creation that invited questions about what came before, about causes and origins. For some, this was uncomfortable, too close to theological concepts of creation. The steady-state model avoided that discomfort by making the universe eternal. No beginning, no end, just an endless cycle of matter and structure arising and dissipating. Observational evidence eventually favored the Big Bang. The discovery of the cosmic microwave background radiation, a faint glow of light coming from all directions, fit perfectly with predictions from Big Bang cosmology. It was the afterglow of the universe's hot, dense infancy, now cooled and stretched into microwave wavelengths. The steady-state theory had no good explanation for this radiation. Gradually, most astronomers came to accept that the universe had a beginning and was evolving over time. But even within the Big Bang framework, theories about galaxy counts varied. How quickly did galaxies form after the Big Bang? Were the first galaxies small and irregular, later merging into larger ones? Or did some large galaxies form quickly? How did dark matter influence the process? These questions affected estimates of how many galaxies existed at different times and how many should be visible today. Computer simulations became important tools for testing theories. Astronomers could input the laws of physics, the properties of matter and dark matter, the rate of cosmic expansion, and watch how structure formed over billions of simulated years. The results were striking. Simulated universes produced cosmic webs, filaments of galaxies separated by voids, structures that matched what observers saw in the real sky. This gave confidence that the theories were on the right track. But simulations also revealed complexity. The number of galaxies depended on how you defined a galaxy. Should you count every small clump of stars as a separate galaxy, or only those above a certain mass? The simulations showed a continuous distribution, from giant galaxies with trillions of stars down to tiny dwarf galaxies with only millions. Where you drew the line affected the count dramatically. Different theories also predicted different distributions. Some models suggested that galaxies were uniformly scattered through space, at least on large scales. Others predicted more clustering, with galaxies gathering into groups and superclusters. Observations showed that clustering was real, that galaxies weren't randomly distributed but followed the invisible scaffolding of dark matter. This meant that counting galaxies required understanding not just numbers but structure, the patterns and relationships that organized cosmic matter. The division of minds wasn't contentious in the way political or personal disagreements might be. It was productive, driving science forward. Each theory made predictions that could be tested. Each astronomer brought different perspectives, different skills, different assumptions. Through their debates and collaborations, a consensus gradually emerged, not because everyone agreed on every detail, but because the weight of evidence pointed in certain directions. By the late 20th century, the mainstream view held that the observable universe contained at least 100 billion galaxies, possibly more. This number came from deep surveys that counted galaxies in sample regions of the sky and extrapolated to the full sphere. It was a staggering number, but it rested on solid methodology and multiple independent observations. Different research groups, using different telescopes and different techniques, arrived at similar conclusions. That convergence suggested the estimate was reliable. But even as consensus formed, uncertainties remained. The faintest galaxies were hard to detect. Dust obscured some regions of the sky. The extrapolations relied on assumptions about the uniformity of the universe. Different teams published slightly different numbers, usually within a factor of 2 or 3 of each other. In astronomy, that's considered good agreement, given the scales involved. But it also meant that the debate wasn't truly settled. The count was still evolving. The theories continued to divide and refine. Today, with new telescopes like James Webb, astronomers are finding galaxies in the very early universe, brighter and more massive than predicted. This forces revisions to models of galaxy formation. Perhaps stars formed more efficiently in the early universe than we thought. Perhaps our understanding of how gas cools and collapses needs adjustment. Each new observation feeds back into theory, sharpening some predictions and challenging others. The division of minds is healthy. It prevents complacency, keeps questions open, drives innovation. Counting galaxies isn't a solved problem passed down from on high. It's an active area of research where passionate, intelligent people can still disagree on details while agreeing on the broad picture. And that broad picture, overwhelming in its implications, is that the universe is filled with galaxies, more than we once imagined, arranged in patterns that reflect the deepest laws of physics, evolving over time in ways we're still learning to understand. The theories may divide, but together they form a richer, more complete vision of cosmic reality. The question had been asked, the theories proposed, now came the hard work of actually counting, of turning speculation into measurement, wonder into data. The investigation that followed would span decades, involving hundreds of astronomers, dozens of telescopes, and millions of hours of observation. It was a pursuit unlike any other, a hunt for light so faint that it barely existed, across distances so vast that they defied imagination. The challenge was immense. Galaxies don't announce themselves. They don't shine steadily like nearby stars. The distant ones appear as faint smudges, barely distinguishable from noise, from cosmic rays hitting the detector, from the glow of our own atmosphere. To count them accurately required instruments of extraordinary sensitivity, techniques of painstaking precision, and patience measured not in days but in years. The first, systematic surveys began in the mid-20th century. Astronomers would select a region of sky, photograph it repeatedly over long exposures, then examine the plates under magnification, marking every possible galaxy by hand. It was tedious work. A single photographic plate might take hours to analyze, and a comprehensive survey required thousands of plates. But slowly, catalogue by catalogue, the count grew. Hundreds of galaxies became thousands. Thousands became tens of thousands. But photographic plates had limits. They could only detect light above a certain threshold. Fainter galaxies simply didn't leave enough of an impression on the emulsion to be visible. Astronomers knew they were missing most of the picture. The pursuit required better tools, more sensitive detectors, longer exposures. It required looking not just at nearby space, but deep into the cosmic past, where the faintest, most distant galaxies hide. The invention of electronic detectors revolutionized the hunt. Charge-coupled devices, or CCDs, could capture light far more efficiently than photographic film. They converted photons directly into electronic signals, which could be measured, stored, and analyzed digitally. A CCD could detect galaxies 10 times fainter than film could show. Suddenly, regions of sky that looked empty through older instruments revealed hundreds of galaxies in CCD images. This technological leap came with new challenges. CCDs were expensive, and the early ones were small, covering only tiny patches of sky. To survey large areas required mosaics of images, carefully stitched together, calibrated so that brightness measurements were consistent across different exposures. The data sets grew enormous. Where once a survey might produce a few hundred photographs to analyze, now it generated millions of individual measurements, far too many for human analysis alone. Computers became essential. Astronomers wrote software to automatically detect galaxies in images, to distinguish them from stars based on their shape and size. A star appears as a point of light, focused by the telescope to the smallest possible spot. A galaxy, being extended, appears slightly fuzzy, spread across multiple pixels. The software could scan images, flag objects that look like galaxies, measure their brightness and position, and compile catalogues automatically. Human astronomers still had to check the results. verify that the software wasn't being fooled by artifacts or noise, but the automation made comprehensive surveys possible for the first time. The pursuit moved to space. Earth's atmosphere, beautiful as it is, interferes with observation. It blurs light, absorbs certain wavelengths, and glows faintly from airglow and scattered sunlight. To see the faintest galaxies, astronomers needed to get above the atmosphere entirely. The Hubble Space Telescope, launched in 1990, provided that vantage point. Orbiting high above Earth, it could capture images of unprecedented clarity, free from atmospheric distortion. Hubble's first deep surveys were revelations. Astronomers pointed it at seemingly blank patches of sky and let it stare for days. The resulting images, the Hubble Deep Field and later the Ultra Deep Field, showed thousands of galaxies in areas smaller than a grain of rice held at arm's length. The pursuit had revealed that the universe was even more crowded with galaxies than the most optimistic estimates had suggested. Every direction, no matter how empty it appeared, was filled with distant light. But the pursuit didn't end there. Each answer led to new questions. How many of these faint galaxies were real, and how many were image artifacts? How far away were they? What were they made of? To answer those questions required spectroscopy, splitting the light of each galaxy into its component wavelengths to measure its redshift, its distance, its composition. This was even more time-consuming than imaging. Where you might photograph thousands of galaxies in a single exposure, you could only take spectra of a few hundred at a time, and each required long integration times to gather enough light. Ground-based telescopes joined the pursuit with innovative techniques. Multi-object spectroscopy allowed astronomers to observe hundreds of galaxies simultaneously by positioning small optical fibers or slits at the location of each galaxy in the field of view. This parallelization accelerated the work dramatically. Surveys like the Sloan Digital Sky Survey mapped millions of galaxies in 3 dimensions, measuring not just their positions on the sky, but their distances, creating a volumetric map of the universe's structure. The pursuit also went beyond visible light. Infrared telescopes could see galaxies hidden by dust, their starlight absorbed and re-emitted at longer wavelengths. Radio telescopes detected hydrogen gas in galaxies, tracing their mass and motion. X-ray observatories spotted the hot gas in galaxy clusters and the radiation from supermassive black holes. Each wavelength added a different view, revealing galaxies that would be invisible at other frequencies. The count had to account for all of them, combining observations across the electromagnetic spectrum. As the data accumulated, patterns emerged. Galaxies weren't scattered randomly. They formed clusters, with dozens or hundreds of galaxies gravitationally bound together. Clusters themselves formed superclusters, connected by filaments of galaxies stretching across hundreds of millions of light years. Between these structures lay voids, vast regions where galaxies were rare. The universe had a foam-like texture, a cosmic web of matter and light surrounding bubbles of near emptiness. Understanding this structure was crucial to counting accurately. If you only surveyed a small region that happened to be in a void, you'd underestimate the total number of galaxies. If you surveyed a cluster, you'd overestimate. The pursuit required surveying, representative volumes large enough to sample all types of environments, from the densest clusters to the emptiest voids. Only then could you extrapolate reliably to the full observable universe. The pursuit also grappled with evolution. Galaxies in the distant past looked different from nearby ones. The early universe had more small, irregular galaxies, while today's universe is dominated by larger, more structured ones. Over billions of years, small galaxies merge into bigger ones, reducing the total count while increasing average size. To count galaxies across cosmic time required understanding this evolution, modeling how populations changed as the universe aged. New telescopes pushed the pursuit deeper still. The James Webb Space Telescope, launched in 2021, has infrared vision sensitive enough to detect galaxies forming in the first few 100 million years after the Big Bang. These early galaxies appear as faint red dots, their light stretched by 13 billion years of cosmic expansion. Finding them requires images even deeper than Hubble's deepest fields, exposures lasting weeks, capturing every precious photon that crosses the vast distance. Each new generation of instruments extends the pursuit. The count climbs higher. Where once we estimated 100 billion galaxies, now we speak of 2 trillion or more. And still, the pursuit continues, because the faintest galaxies remain undetected, hidden just below the threshold of current technology. Future telescopes will find them, pushing the count higher still. The pursuit may never end, because there's always a fainter object, always a deeper layer, always one more galaxy hiding in the dark. But the pursuit isn't just about reaching a final number. It's about the process of discovery itself, the methodical work of gathering light, analyzing data, testing hypotheses. It's about collaboration across continents and decades, as one generation of astronomers builds on the work of the previous. It's about the technology developed along the way, detectors and algorithms and telescopes that advance not just astronomy but all of science. And there's something deeply human about the pursuit. The dedication to counting what seems uncountable, to measuring what seems infinite, speaks to a fundamental aspect of who we are. We're curious. We ask questions even when the answers seem beyond reach. We build tools to extend our senses, and when those tools reveal something unexpected, we build better ones. The pursuit of counting galaxies is really the pursuit of understanding, of bringing the distant close, of making the invisible visible. The investigation continues tonight as you listen to these words. Somewhere, a telescope is collecting light from a galaxy billions of light years away. Somewhere, an astronomer is analyzing data, refining the count, checking calculations. The pursuit never sleeps because the universe never stops revealing itself. And with each new galaxy added to, the catalogue, our picture of the cosmos, becomes a little more complete, a little more wondrous, a little more real. The light arrives in silence, one photon at a time, crossing the vast emptiness between galaxies. Each photon carries information, encoded in its wavelength, its energy, its direction of travel. When it finally strikes a detector, after journeys lasting millions or billions of years, it becomes data, a number, a signal, a clue about the object that sent it. This is how we count galaxies, not by touching them or traveling to them, but by collecting their light and learning to read what it tells us. The data comes in many forms. The most basic is an image, a two-dimensional map of light captured over some period of time. Each pixel in the image records how many photons arrived at that location during the exposure. Bright pixels indicate intense light sources. Dim pixels suggest faint ones or empty space. But raw images are messy. They contain noise from the detector itself, cosmic rays that strike randomly, scattered light from nearby stars or the atmosphere. Before the data can reveal galaxies, it must be cleaned, calibrated, processed. Calibration is crucial. The detector doesn't respond uniformly across its surface. Some pixels are more sensitive than others. Temperature affects the readings. Time degrades the equipment. To turn raw data into meaningful measurements, astronomers must account for all these factors. They take calibration images, exposures with the telescope pointed at nothing in particular or with the shutter closed, to measure the detector's baseline response. They observe standard stars, objects whose brightness is precisely known, to establish a brightness scale. Only after all these corrections can the data be trusted. Once calibrated, the image reveals its secrets. Software scans the pixels, looking for patterns that match what a galaxy should look like. A cluster of adjacent bright pixels, extended rather than point-like, with a brightness profile that falls off gradually from center to edge. Each detection is assigned coordinates, a position on the sky measured in degrees, minutes, and seconds. It's given a brightness, usually expressed in magnitudes, the traditional astronomical unit, where smaller numbers mean brighter objects, and each magnitude represents a factor of about 2.5 in brightness. But brightness alone doesn't tell you much. A galaxy might look faint because it's truly dim, or because it's very far away. To distinguish these possibilities, you need distance, and that requires more data. Specifically, it requires spectroscopy, spreading the galaxy's light into a spectrum, a rainbow showing how much light arrives at each wavelength. The spectrum contains a wealth of information. Absorption lines appear where elements in the galaxy's stars absorb specific wavelengths. Emission lines show where gas glows, and the positions of these lines reveal the galaxy's redshift. Redshift is the key to distance. Light from galaxies moving away from us is stretched, shifted toward longer, redder wavelengths. The amount of shift tells you how fast the galaxy is receding, and thanks to the expansion of the universe, recession speed is directly related to distance. A galaxy with a small redshift is relatively nearby. One with a large redshift is far away, possibly billions of light years distant. By measuring redshift, astronomers can place each galaxy in three-dimensional space, turning a flat image into a volumetric map. Collecting spectra is time-consuming. You must position the galaxy precisely in the telescope's field of view, split its faint light through a grating or prism, and expose for long enough to gather sufficient signal. For very faint galaxies, this might take hours. Early surveys could only measure spectra for the brightest galaxies, leaving the majority of their distance unknown. But techniques improved. Multi-object spectrographs could observe hundreds of galaxies simultaneously. Automated pipelines processed the data, identifying redshift by comparing observed spectra to templates. The data also includes colors, measurements of brightness in different filters. A filter passes only certain wavelengths, allowing astronomers to see how much blue light a galaxy emits versus red light. Color reveals age and composition. Young galaxies with active star formation shine brightly in blue from hot, massive stars. Old galaxies, where star formation has ceased, glow predominantly red from cooler, longer-lived stars. By measuring colors, astronomers can classify galaxies, grouping them by type, and estimate their properties even without detailed spectra. Photometric redshift, a technique that estimates distance from colors alone, became important as surveys grew larger. While less precise than spectroscopic redshift, photometric methods could be applied to every galaxy in an image, not just the bright ones. By comparing a galaxy's brightness across multiple filters to models of how galaxy light changes with redshift, astronomers could estimate distance with reasonable accuracy. This allowed surveys to count galaxies in 3 dimensions, even when spectra weren't available for all of them. The data revealed unexpected diversity. Galaxies come in an enormous range of sizes, from dwarfs containing millions of stars to giants with trillions. They vary in color, from deep red to brilliant blue. Some are perfectly symmetrical spirals, others are amorphous blobs, Some are solitary, drifting alone through the void. Others cluster together, interacting gravitationally, sometimes colliding and merging. Each galaxy is unique, yet patterns emerge when you examine thousands or millions of them. The data shows that while each galaxy tells its own story, they all follow the same fundamental laws. Size measurements are tricky. Galaxies don't have sharp edges. Their brightness fades gradually into the background, asymptotically approaching zero but never quite reaching it. Where do you draw the boundary? Astronomers use conventions, measuring size to the point where brightness drops to some threshold level, or fitting mathematical models to the brightness profile. These measurements are consistent enough to compare galaxies to each other, but they carry uncertainty. Faint outer regions might be too dim to detect, leading to underestimates of true size. The data also includes morphology, the shape and structure of galaxies. Edwin Hubble's classification system, created in the 1920s, divided galaxies into spirals, ellipticals, and irregulars. Spirals were further classified by how tightly their arms wound and how prominent their central bulge was. Ellipticals by how elongated they appeared. The scheme, while simple, captured real physical differences. Modern surveys classify millions of galaxies automatically using computer algorithms, but many still reference Hubble's original categories. Deep fields provided especially rich data. By staring at tiny patches of sky for extended periods, astronomers collected enough light to see galaxies too faint for standard surveys. These deep images showed not just more galaxies, but different types. The faintest objects were often small, irregular, or distorted, galaxies caught in the act of forming or merging. They look different from the mature spirals and ellipticals that dominate nearby space. The data suggested that galaxy populations evolve over time, that the early universe was wilder, more chaotic, filled with smaller, actively forming systems. Each piece of data, each measurement, is a fragment. A single galaxy observed once gives you position and brightness. Add a spectrum and you get distance, velocity, composition. Add multi-wavelength observations and you learn about star formation, dust content, the presence of a central black hole. Combine data from many galaxies and patterns emerge. Distributions, correlations, trends. The fragments to assemble into a larger picture, like a mosaic where each tiny tile contributes to the overall image. The data also includes non-detections. Sometimes you look at a region and find nothing. Those voids are informative too. They tell you where galaxies aren't, constraining models of structure formation. If simulations predict galaxies in a location, but observations find none, the models need adjustment. Absence of evidence is not evidence of absence in most contexts, but in astronomy, where observations are systematic and comprehensive, empty spaces carry meaning. Errors are ever present. Every measurement has uncertainty, a range of possible true values. Faint objects have larger errors because fewer photons were collected. Distance estimates from photometric redshift can be off by 10 or 20%. Even spectroscopic redshifts have small uncertainties. Astronomers account for these by reporting error bars, by running Monte Carlo simulations that propagate uncertainties through calculations, by cross-checking results with independent observations. The data is never perfect, but it's good enough to draw robust conclusions when treated carefully. Archiving data is crucial. Modern surveys generate petabytes of information, far more than any individual astronomer could analyze. Public archives make this data available to the entire community. Years after a survey completes, researchers return to the archive, asking new questions, applying new techniques, extracting insights the original observers never anticipated. The data has lasting value, a resource for future generations. Each observation adds to humanity's collective knowledge, a permanent record of how the universe appears from Earth at this moment in time. The clues and fragments continue to accumulate. New telescopes add new data. Improved algorithms extract more information from old data. Slowly, piece by piece, the picture becomes clearer. We don't see every galaxy, we never will, but we see enough to estimate the total, to understand the distribution, to trace the story of how structure formed and evolved. The data, imperfect and incomplete as it is, connects us to the distant universe, turning light into knowledge, photons into understanding. Each number is a thread, and together they weave the tapestry of cosmic reality. For every galaxy we can see, shining brightly in the darkness, there are others that hide. Not because they're far away, though distance certainly plays a role, but because they've chosen invisibility. They contain few stars, little light, almost nothing that would catch our eye or our instruments. Yet they exist, massive and real, held together by forces we can't see, shaped by matter that refuses to glow. These are the dark galaxies, the hidden structures that remind us how much of the universe remains beyond our direct perception. The realization came gradually, like a shadow emerging from fog. Astronomers studying the motion of visible galaxies noticed something wrong. The stars at the edges of spiral galaxies move too fast. According to Newton's laws, objects farther from the center should orbit more slowly, just as outer planets in our solar system take longer to complete their orbits than inner ones. But galaxies didn't follow that pattern. Stars far from the center move just as quickly as those closer in, sometimes faster. The only explanation was invisible mass. Something beyond what we could see was adding gravity, pulling on those outer stars, speeding them up. That something became known as dark matter, and its presence changed everything. Galaxies weren't just collections of stars and gas. They were embedded in enormous halos of invisible material, extending far beyond the visible edge, dominating the total mass. What we saw, the bright spiral or elliptical shape, was only the tip of a much larger structure. At first, dark matter was theoretical, invoked to explain observations but not directly detected. But the evidence accumulated from multiple sources. Gravitational lensing showed that light from distant galaxies was bent by invisible mass in galaxy clusters, far more mass than the visible matter could account for. The motion of galaxies within clusters indicated that something unseen was holding them together. Computer simulations of structure formation only worked if dark matter was included. Without it, the cosmic web wouldn't form correctly. Galaxies wouldn't match observations. The deeper mystery is that we still don't know what dark matter is. It's not made of atoms. It doesn't emit or absorb light. It doesn't interact with normal matter except through gravity. Various candidates have been proposed, exotic particles with names like WIMPs and axions, but none have been conclusively detected despite decades of searching. Dark matter remains invisible, not just in practice but in principle. It's a substance known only by its effects, a presence felt but never seen. This invisible component makes counting galaxies far more complex. When we count, are we counting only the visible parts, the stars and gas that shine? Or should we include the dark halos, the massive structures that contain most of the mass? Some regions of space might host dark galaxies, halos with few or no stars, invisible to conventional surveys but detectable through their gravitational influence. How many of those exist? If they outnumber visible galaxies, then our counts are dramatically incomplete. Recent observations have found evidence of these ghostly structures. Astronomers using radio telescopes detected clouds of hydrogen gas moving through space, rotating as if bound by gravity, but with no visible stars. These dark galaxies contain gas but haven't yet formed stars, or formed so few that they're essentially invisible. They're like seeds, structures waiting to ignite, or perhaps failed galaxies that never quite managed to turn their gas into stars. Either way, they exist, and they challenge our definitions. Is a galaxy still a galaxy if it doesn't shine? There are also ultra-diffuse galaxies, objects so spread out that their light is incredibly faint. They have the mass of significant galaxies, but stretched across such a large volume that they barely register in images. Hundreds could hide in regions we thought were empty, their faint glow lost in the background. Only careful searches, stacking multiple images or using specialized techniques, reveal them. Each discovery suggests that the universe's faint end is far more populated than we realized. The hidden truth extends beyond dark matter and faint galaxies. There's also the question of what lies beyond our observational horizon. The universe we can see is limited by the speed of light and the age of the cosmos. Light from more distant regions hasn't had time to reach us yet. Those regions presumably contain galaxies, following the same rules as the ones we can see, but we can't count them. They exist in a space that's real but forever inaccessible, hidden not by darkness but by distance and time. Some cosmologists suggest the universe might be infinite. If so, then the number of galaxies is also infinite, and the question of counting becomes meaningless. We can only count what's observable, a finite bubble around us, knowing that beyond it lies endlessness. The hidden truth, then, is that the total is unknowable, not because our instruments are inadequate, but because infinity can't be measured. There's also the mystery of dark energy, a force that makes up about 70% of the universe's content. Unlike dark matter, which pulls things together through gravity, dark energy pushes them apart, accelerating cosmic expansion. Its nature is even less understood than dark matter. Is it a property of space itself? A cosmological constant, as Einstein once proposed? Or is it a dynamic field that changes over time? The answer affects how we count galaxies over cosmic history and how the universe will evolve in the future. The deeper you look, the more layers of mystery appear. Every answer opens new questions. We thought galaxies were simple, islands of stars in the dark, but they're complex systems, built on invisible scaffolding, shaped by forces we barely understand, existing in a universe that might extend forever beyond our sight. The hidden truth is that what we see is a fraction of what exists, and what exists might be a fraction of what's possible. This realization is humbling but also thrilling. It means there's always more to discover, always another layer beneath the surface. The visible galaxies, as numerous and magnificent as they are just the beginning. Behind them, supporting them, shaping them, lies a deeper reality, dark matter halos that dwarf the galaxies they contain, dark energy that determines the universe's fate, faint and dark galaxies that outnumber the bright ones, regions beyond our horizon that we can never see. Counting galaxies, then, is counting only what shines. It's measuring the luminous tip of a much larger iceberg. The true census would have to include everything, visible and invisible, near and infinitely far. But such a census is impossible. We work with what we have, knowing it's incomplete, hoping that the sample we can measure represents the whole. It's a leap of faith, justified by the uniformity of physics. If the laws are the same everywhere, then what we see here should reflect what exists everywhere else. The hidden truth reminds us that the universe doesn't reveal itself easily. It holds secrets, layers of reality that require not just better telescopes but new ways of thinking. Dark matter was invisible until we learned to look at motion rather than light. Dark energy was hidden until we measured cosmic expansion precisely. What other mysteries remain hidden, waiting for the right question, the right instrument, the right insight? Perhaps the deepest mystery is why the universe contains anything at all. Why? Is there structure, galaxies, stars, rather than uniform emptiness? The answer lies in quantum fluctuations in the earliest moments after the Big Bang, tiny variations in density that gravity amplified over billions of years. But that just pushes the question back. Why those particular fluctuations? Why those laws of physics? The hidden truth touches on the profound, on questions that blend science and philosophy, questions about origins and existence itself. For now, we count what we can. We catalogue the visible galaxies, estimate the dark ones, acknowledge the unknowable. The deeper mystery doesn't frustrate the counting, it enriches it. Every galaxy we observe is part of a larger pattern, a structure built on invisible foundations. To count them is to glimpse that structure, to sense the presence of something vast and hidden. The light we see connects to the darkness we don't, and together they form the universe. Complete and mysterious, known and forever unknowable. There are moments in science when everything changes, when a single observation or experiment shifts the entire foundation of understanding. These turning points are rare, often unexpected, and always profound. In the quest to count galaxies, that moment came in 1995, when astronomers pointed the Hubble Space Telescope at what appeared to be absolutely nothing and discovered everything. The decision itself was controversial. Telescope time on Hubble was precious, allocated carefully among hundreds of competing proposals. To spend 10 consecutive days staring at a single, tiny patch of blank sky seemed wasteful to some. There were so many known objects to study, so many questions that could be answered with targeted observations. Why waste time on emptiness? But Robert Williams, the director of the Space Telescope Science Institute at the time, had a vision. He wanted to see how deep they could go, how faint the detectable galaxies might be if they simply looked long enough. He chose a region in the constellation Ursa Major, near the Big Dipper's handle, that contained no bright stars, no known galaxies, nothing that would interfere with the observation. It was a random spot, representative of the average sky. If they found galaxies there, then galaxies must exist everywhere. The exposure lasted over 10 days in total, spread across multiple sessions. The telescope stared unblinking at that small patch, about 1/24 millionth of the entire sky, an area you could cover with a grain of sand held at arm's length. Photons accumulated slowly, building up signal in the detector. Hours became days. Days stretched into what felt like an eternity of waiting. What would they find? Maybe a few dozen galaxies, maybe 100 if they were lucky. When the final image was processed, the scientific community gasped. The blank patch wasn't blank at all. It was crowded. Nearly 3,000 galaxies filled that tiny window, each one a separate system of stars, each one billions of light years away. Spirals, ellipticals, irregular shapes, galaxies in every stage of evolution, from young and actively forming stars to old and quiet. The image was a revelation, a glimpse into the true density of the cosmic population. The turning point wasn't just the number of galaxies found, it was what those galaxies represented. If a random patch of seemingly empty sky contained 3,000 galaxies, then simple multiplication suggested the full sky must contain billions. possibly hundreds of billions. The previous estimates, already large, suddenly seemed conservative. The universe was even more populated than the most optimistic projections had suggested, but the deeper impact came from the realization that emptiness doesn't exist. Every direction you look, no matter how carefully you choose a blank region, contains galaxies. The darkness of space is an illusion created by distance and faintness. The universe is saturated with structure. There are no voids, only regions where galaxies are harder to see. This fundamental truth changed how astronomers thought about cosmic density and the distribution of matter. The Hubble Deep Field image became iconic. It appeared in textbooks, museums, public presentations. People who had never looked through a telescope were moved by it. Here was direct evidence of the universe's abundance, a visual demonstration that we live in a cosmos overflowing with galaxies. Each faint smudge in the image represented billions of stars, possibly trillions of planets. The scale was overwhelming and beautiful. The image also revealed cosmic history layered in light. The nearest galaxies in the deep field appeared as they were a few 100 million years ago. The farthest ones showed the universe as it existed more than 12 billion years in the past, less than 1 billion years after the Big Bang. Looking at the image was like looking at a timeline, with different galaxies representing different epochs. The universe's evolution played out across that small frame, from the chaotic early days of galaxy formation to the more structured present. Astronomers immediately began analyzing the data. They measured the brightness and colors of each galaxy, estimated their distances, classified their shapes. Patterns emerged. Galaxies at different distances had different properties. Distant ones were smaller, bluer, more irregular, consistent with theories of hierarchical structure formation, where small galaxies merge over time to form larger ones. The deep field provided direct observational support for cosmological models, confirming predictions and constraining parameters. The success of the deep field led to follow-ups. In 2004, the Hubble Ultra Deep Field went even deeper, exposing for longer, detecting fainter galaxies. It found about 10,000 galaxies in an even smaller patch of sky. Later campaigns in different directions confirmed the results were representative. No matter where you looked, the density was consistent. The universe looked the same in all directions, a principle called isotropy that's fundamental to modern cosmology. The turning point changed the conversation around counting galaxies. Before the deep field, estimates were uncertain, debated, based on extrapolations from limited samples. After, the evidence was undeniable. The universe contained at least 100 billion galaxies, probably more. The deep fields provided the calibration points, the ground truth against which all other surveys could be measured. They set a lower bound on the count, a number that every subsequent estimate had to exceed or explain. But the deep field also revealed how much we were missing. The faintest galaxies in the image were at the very edge of detection, barely registering above noise. How many fainter galaxies existed just below that threshold? How many were too small, too diffuse, too distant for even Hubble's deep gaze? The image suggested that for every galaxy we could see, there might be several we couldn't. The count would have to be revised upward again. The paradigm shift wasn't just scientific, it was psychological. Before the deep field, the universe felt large but comprehensible. After, it felt infinite. The image destroyed any remaining sense that we had a complete picture. It showed that the cosmos is always deeper than we think, always more populated, always ready to surprise us with its abundance. The turning point was the moment we accepted that counting galaxies would never be finished. that the total would always grow as our instruments improved. This shift affected how research was conducted. Surveys became more ambitious, covering larger areas, going deeper. If random patches contained thousands of galaxies, then comprehensive mapping could catalogue millions, tens of millions. Projects like the Sloan Digital Sky Survey scaled up dramatically, motivated by the knowledge that the universe's richness justified effort. The deep field proved that the investment in large-scale surveys would pay off in data and discovery. The turning point also touched the public imagination. Images of the deep field went viral. Before viral was a common term, people shared them, discussed them, felt something shift in their understanding of existence. The image made the abstract concrete. You could see the galaxies, each one distinct, each one real. It wasn't theoretical anymore. The universe's abundance was visible, undeniable, beautiful. For many, it was a spiritual moment, a glimpse of something greater than human concerns or earthly troubles. Astronomers who worked on the deep field describe it as a career-defining moment. They knew they were seeing something no one had seen before, that they were opening a new window on the cosmos. The excitement in the research community was palpable. Conferences buzzed with discussions of the implications. Papers poured out, analyzing every aspect of the data. The deep field became a benchmark, a standard against which all other observations were compared. Even now, decades later, the deep field retains its power. The image hasn't been surpassed in cultural impact, though deeper images have been taken. It represents a moment when humanity collectively realized just how vast the universe truly is. The turning point it created continues to ripple through astronomy, shaping research priorities, informing public outreach, reminding us that the quest to count galaxies is really the quest to understand our place in an unimaginably large and ancient cosmos. The paradigm shifted. What looked empty was full. What seemed large became larger still. And the question of how many galaxies exist transformed from speculation to serious science, grounded in observation, driven by evidence, reaching toward truth. When a stone drops into still water, the ripples spread outward, each circle expanding from the center of impact. The Hubble Deep Field was that stone, and the consequences of its revelation spread through astronomy like waves, touching every corner of the field, reshaping research priorities, changing how we think about the universe and our methods of exploring it. The most immediate consequence was observational. If that one random patch of sky contained nearly 3,000 galaxies, then astronomers needed to survey more patches to confirm that the result wasn't a statistical fluke. Telescope proposals flooded in, each requesting deep exposures of different regions. Within a few years, multiple deep fields had been observed, in different directions using different wavelengths. Each confirmed the original result. The universe was uniformly dense with galaxies. The ripple of verification spread, solidifying confidence in the new count. Research programs shifted focus. Before the deep field, much effort went into studying nearby galaxies in detail, mapping their structure, understanding their dynamics. That work continued, but a new priority emerged, studying the faint, distant galaxies that the deep field had revealed. These objects represented the early universe, galaxies in formation, systems we could never observe in the nearby cosmos because they'd already evolved into something else. They were windows into cosmic youth, and everyone wanted to look through them. The consequence for technology was immediate. The deep field demonstrated what space-based telescopes could achieve, free from atmospheric distortion. It validated the investment in Hubble and motivated support for future missions. Plans for the James Webb Space Telescope, already in development, gained momentum. If Hubble could see galaxies from 12 billion years ago, then Webb, with its larger mirror and infrared sensitivity, might see even earlier ones, from the universe's first few 100 million years. The ripple of the deep field helped secure funding and public enthusiasm for the next generation of observatories. Computing infrastructure felt the impact too. The deep field generated enormous amounts of data, millions of measurements from thousands of galaxies. Analyzing it all required powerful computers and sophisticated software. Astronomy became a data science, a field where computational skills were as important as observational ones. Universities invested in computing resources, trained students in programming and statistics, built pipelines to process images automatically. The ripple of data-driven astronomy spread beyond galaxy counting, affecting how all astronomical research was conducted. Theoretical models also adjusted. Before the deep field, simulations of galaxy formation had to match a relatively small number of observed galaxies. After, they had to reproduce not just the count, but the distribution of galaxy types, sizes, and brightnesses revealed in the deep images. Some models succeeded, others failed, and were revised or discarded. The observational constraint tightened, forcing theories to become more accurate, more predictive. The ripple of better data led to better models, which in turn predicted new observables, creating a feedback loop of improvement. The consequence for cosmology was profound. The deep field provided evidence for the cosmic expansion in a new way. By measuring the redshifts of galaxies at different distances, astronomers could trace how fast the universe was expanding at different times in its history. The data supported the lambda CDM model, the standard cosmology that includes dark matter and dark energy. It constrained parameters like the universe's age, composition, and fate. The ripple of the deep field reached the most fundamental questions in physics, about the nature of space, time, and existence itself. Educational programs incorporated the deep field immediately. Textbooks updated to include the image and its implications. Planetariums built shows around it. Teachers used it to inspire students, to show them that astronomy wasn't just about looking at pretty pictures, but about making genuine discoveries that changed human understanding. The ripple of inspiration touched a generation, some of whom would grow up to become the astronomers, using even more powerful telescopes to push the boundaries further. Public perception shifted subtly but significantly. Before the deep field, galaxies were abstract, distant things most people never thought about. After, they became real, visible, countable. The image made the universe's scale tangible. When people looked at it, they saw not just galaxies but evidence of a cosmos far larger and older than everyday experience suggested. The ripple of awareness spread through culture, appearing in art, literature, music, influencing how we tell stories about existence and our place within it. The consequence for philosophy and theology was less immediate but no less real. Religious thinkers grappled with what it meant that the universe contained hundreds of billions of galaxies. Did this vastness diminish humanity's importance or enhance it? Was the abundance a sign of waste or generosity? Different traditions found different answers, but the questions themselves shifted. The ripple of the deep field touched conversations about meaning, purpose, and the relationship between the cosmic and the personal. International collaboration increased as a consequence. The deep field demonstrated what could be achieved with coordinated effort and shared resources. Astronomers from different countries worked together on follow-up observations, combining data from multiple telescopes, pooling expertise. The ripple of cooperation spread, establishing patterns of collaboration that continue to define how large astronomical projects are conducted. Science became more global, more connected, more aware that the questions we ask about the universe require collective effort to answer. The economic consequence was also notable. The deep field showed that investment in basic science paid dividends in knowledge and technology. Funding agencies pointed to it as justification for supporting astronomy. The techniques developed to process deep field images found applications in medical imaging, satellite reconnaissance, and other fields. The ripple of innovation spread beyond astronomy, benefiting society in unexpected ways. The deep field became a case study in how curiosity-driven research generates practical value. Graduate students flocked to the field. Astronomy departments saw applications surge as young scientists wanted to be part of the deep field revolution. The ripple of enthusiasm created a generation of researchers trained in the new techniques, skilled in the new tools, ready to take on the challenges of counting and understanding galaxies. Their work over subsequent decades built on the foundation the deep field established, pushing knowledge ever deeper. The psychological consequence shouldn't be underestimated. For many astronomers, the deep field was a moment of validation. Years of work, of arguing for deeper surveys, of pushing against skepticism, paid off spectacularly. The ripple of vindication spread through the community, energizing research, encouraging bold proposals, fostering a culture where ambitious projects were supported rather than dismissed as unrealistic. The field gained confidence, a sense that if we just looked hard enough, the universe would reveal its secrets. Museum exhibits featured the deep field prominently. Visitors stood before giant prints of the image, contemplating its implications. Some felt awe, others felt insignificance. Many felt both simultaneously. The ripple of contemplation touched millions, making abstract cosmology personal, connecting individual viewers to the vastness of existence. The deep field became one of those rare scientific images that transcended its field, becoming part of the broader cultural conversation about who we are and where we are. The immediate ripples from the deep field spread in all directions, touching science, technology, education, culture, philosophy. Each ripple created others, waves overlapping, reinforcing, generating patterns of change that continued long after the initial observation. The consequence wasn't just a new count of galaxies, it was a new way of seeing, a new appreciation for the universe's richness, a new commitment to exploring the depths. The stone had dropped, the water rippled, and the surface would never be still again. Some discoveries fade as new ones supersede them. Others resonate across decades, their impact growing rather than diminishing with time. The Hubble Deep Field belongs to the latter category. Nearly 3 decades after that image was first released, its echoes still reverberate through astronomy, shaping how we observe, how we think, how we understand the cosmos, and our place within it. The long-term impact on galaxy surveys has been transformative. Every major survey conducted since the deep field owes something to its approach. Go deep rather than wide. Prioritize faint objects over bright ones. Let the telescope stare until the invisible becomes visible. The philosophy of deep imaging has become standard. Surveys now routinely include deep components, dedicated observations that push toward the detection limit, seeking the faintest galaxies at the edge of cosmic time. The count itself has evolved over time, shaped by the deep field's legacy. In the years following its release, the estimate of galaxies in the observable universe climbed from tens of billions to over 100 billion. Then, as follow-up observations went deeper and surveys covered more area, the count climbed again. By 2016, a careful analysis suggested the number might be closer to 2 trillion, 20 times higher than earlier estimates. Each revision traced back to the deep field's core insight that faint galaxies vastly outnumber bright ones. that the universe is more crowded than it appears. The impact on our understanding of galaxy evolution has been equally profound. The deep field showed galaxies at many different stages of development, from young, irregular systems just beginning to form stars to mature spirals and ellipticals. By studying how galaxy properties change with distance, which also means with time, astronomers piece together an evolutionary picture. Small galaxies merge to form larger ones. Star formation was more vigorous in the early universe. The population of galaxies today is different from the population billions of years ago. These insights came directly from deep field observations and their successors. The technological impact echoes still. The techniques developed to process deep field data, to detect faint objects in noisy images, to calibrate photometry precisely, to measure colors and morphologies automatically, all these became standard tools used across astronomy. Software packages originally written to analyze the deep field now analyze everything from asteroids to exoplanets. The ripples of innovation spread far beyond galaxy counting, improving astronomical research across the board. Educational impact persists across generations. Students who were children when the deep field was released are now professional astronomers, teaching the next generation. The image appears in virtually every introductory astronomy textbook, every planetarium show about cosmology, every public lecture on the universe's scale. It's become the visual representation of cosmic abundance, the standard illustration of what lies beyond our visible horizon. Its impact on how we teach and learn about the universe is incalculable. The philosophical impact has deepened with time. The deep field forced a reckoning with scale, with the sheer number of galaxies and stars and potential planets. That reckoning continues. Conversations about extraterrestrial life, about humanity's significance, about the relationship between the vast and the small, all reference the abundance the deep field revealed. It changed not just what we know, but how we think about knowing, about our capacity to comprehend the incomprehensibly large. Cultural impact manifests in unexpected places. The deep field inspired artists, musicians, poets. Its structure, the random scatter of galaxies across the frame, became a motif in visual art. Its implications, the hint of infinite vastness, influenced literature and film. Science fiction writers referenced it, building stories around the idea that every faint smudge might harbour civilizations. The image escaped the confines of scientific publications and entered the broader cultural imagination, becoming a symbol of exploration and wonder. The impact on subsequent missions has been direct. The success of the deep field ensured support for Hubble's extensions and upgrades, which allowed even deeper observations. It influenced the design specifications for the James Webb Space Telescope, ensuring that telescope would have the infrared sensitivity needed to see even earlier galaxies. Webb's first deep field, released in 2022, echoed the original Hubble image, but showed the universe at even greater distances. Galaxies from the first few 100 million years after the Big Bang. The legacy continues, each generation building on the last. International competition and cooperation both increased as a consequence. Different countries wanted their own deep field observations, their own contributions to mapping the universe. European, Asian, and American telescopes all conducted deep surveys, sometimes competing, sometimes collaborating, always pushing toward fainter, more distant galaxies. The impact on the global scientific community was to create a shared goal, a common frontier that united efforts across borders and cultures. The impact on dark matter research was indirect but significant. The deep field showed where visible galaxies were, which allowed better mapping of where dark matter must be. By combining deep field observations with gravitational lensing measurements, astronomers created three-dimensional maps of dark matter distribution, testing models of structure formation. The visible galaxies traced the invisible scaffolding, and the deep field provided the visible data that made those maps possible. Public investment in astronomy increased, partly due to the deep field's impact. Funding agencies could point to the image as a return on investment, a tangible result from spending on space telescopes and observatories. The public enthusiasm it generated translated into political support for science budgets. The impact on the sociology of science funding was subtle but real, establishing deep surveys as worthy of major resources, justifying the construction of ever larger and more expensive facilities. The impact on how we answer the question, how many galaxies are there, has been fundamental. Before the deep field, estimates were educated guesses based on limited data. After, they became statistically rigorous extrapolations grounded in comprehensive sampling. The methodology the deep field established, of selecting representative patches, going as deep as possible, and scaling to the full sky, remains the standard approach. Every modern galaxy count follows that blueprint. The echo through time also includes what hasn't changed. The sense of wonder that accompanied the first view of the deep field remains every time someone encounters it for the first time. The image hasn't lost its power to astonish, to make people pause and contemplate their relationship to the universe. That emotional impact, that capacity to inspire awe, is perhaps the most enduring legacy. Decades from now, when even deeper fields have been captured, when galaxy counts have been refined further, the original Hubble Deep Field will still resonate, will still remind us of the moment when the universe revealed just how full and rich it truly is. The impact of the deep field will echo as long as astronomy exists. It represents a turning point, a before and after in our understanding. What we learned from it, staring at seemingly empty darkness, reveals abundance beyond imagination. The echoes carry forward, touching each new generation of astronomers. Each new telescope pointed toward the depths, each person who looks at the image and wonders what it means to live in a universe so vastly populated. Time passes, knowledge grows, but the deep field's impact endures. A stone whose ripples never quite fade, a discovery whose consequences continue to unfold. Behind every galaxy counted, behind every observation recorded, behind every image captured and analyzed, there are people, human beings with curiosity and patience, dedication and doubt. People who spend their lives looking upward, asking questions that have no easy answers. The story of counting galaxies is ultimately a story about dreamers, about those who chose to pursue the impossible simply because it called to them. Edwin Hubble, whose name has appeared so often in this story, was one such dreamer. He began his career studying law, following a more practical path, but astronomy pulled him back. He abandoned a conventional future to spend cold nights at a telescope, measuring light from objects so distant they barely registered on photographic plates. His decision to measure the distance to Andromeda wasn't assigned by some grand authority. It came from his own curiosity, his own drive to know what those spiral nebulae really were. He chose the harder path because it led toward truth. Henrietta Leavitt, whose discovery of the relationship between Cepheid period and luminosity made Hubble's measurement possible, never received the recognition she deserved during her lifetime. She worked as a human computer at Harvard Observatory, one of many women hired to analyze photographic plates because they could be paid less than men. Despite the barriers and indignities, she pursued the patterns she saw in the data, published her findings, and created the cosmic measuring stick that would expand the known universe. She was a dreamer who persisted despite a system that undervalued her contributions. Robert Williams, who decided to point Hubble at blank sky for the deep field, took a professional risk. Many colleagues thought the project was wasteful. Telescope time was precious. Why spend it on emptiness? But Williams had a vision of what might be there, hidden in the faint light, waiting to be revealed. He used his position as director to allocate the time, defending the decision even as criticism mounted. When the results came in, proving him right in spectacular fashion, he didn't gloat. He simply marveled at what they'd found, grateful that curiosity had been allowed to lead. These prominent names are joined by countless others whose contributions are less celebrated but no less essential. The graduate students who spent years analyzing single deep field images, measuring the properties of thousands of galaxies one by one. The telescope operators who guided instruments through long cold nights, making minute adjustments to keep targets centered. The software engineers who wrote code to process data, turning raw photons into meaningful measurements. The theorists who built models, testing hypotheses, comparing predictions to observations, each person a dreamer in their own way, contributing their particular skills to the collective effort. There's something profoundly human about the decision to count galaxies. It's not practical. It doesn't solve immediate problems or generate obvious profits. It satisfies no physical need. Yet people devote careers to it, spending decades in pursuit of better measurements, more accurate counts, deeper understanding. What drives that dedication? Perhaps it's the same impulse that made our ancestors look up at the night sky and wonder, the desire to know, to understand, to place ourselves within the larger context of existence. That impulse is fundamentally human, appearing across cultures and throughout history. The sacrifices are real. Astronomers often work odd hours when telescopes are scheduled. They travel to remote observatories in deserts and on mountaintops, far from family and comfort. The work can be tedious, analyzing data that reveals nothing new more often than it reveals something exciting. Grant proposals get rejected, papers face criticism, careers advance slowly, if at all. Yet they persist because the questions matter more than the difficulties. The dreamers aren't naive about the challenges. They simply value the pursuit enough to accept them. Many describe moments of profound connection, times when the work transcends its technical details and touches something deeper. Looking at a spectrum and realizing you're seeing light that left its source before Earth existed, identifying a galaxy in an image and understanding that you're the first person ever to see this particular collection of stars, calculating a distance and grasping how far light had to travel to reach your detector. These moments of awareness, when the cosmic scale becomes personal, sustain the dreamers through the long stretches of routine work. The human element includes failure and frustration. Not every observation succeeds. Weather interferes. Instruments malfunction. Calculations contain errors that take months to find. Promising results turn out to be artifacts. Theories that seemed elegant fail to match observations. The path to knowledge is not straight. It wanders, backtracks, sometimes hits dead ends. The dreamers learn to accept failure as part of the process, to start over, to try again with different approaches. Resilience becomes as important as intelligence. Collaboration is essential. No single person counts all the galaxies. It takes teams, institutions, international partnerships. The dreamers learn to work together, to share data, to build on each other's findings. Egos must be set aside, at least partially. Credit must be shared. The best discoveries often come from combining perspectives when someone trained in observation teams with someone skilled in theory, when different specializations merge to illuminate problems from multiple angles. The human element is social as well as individual. There's also competition, though usually friendly. Different teams race to be first with new results. Telescope proposals compete for limited time. Papers compete for publication in prestigious journals. This competition can drive innovation, pushing everyone to work harder, think more creatively, check more carefully. But it can also create pressure, stress, occasionally conflict. The dreamers navigate these dynamics, balancing ambition with cooperation, individual recognition with collective progress. Many speak of astronomy as a calling rather than a career, something they couldn't not do, regardless of obstacles. The universe's mysteries exerted a pull too strong to resist. They might have been talented in other fields, could have pursued more lucrative or stable paths, but they chose stars and galaxies instead. That choice reflects something essential about human nature, our need for meaning beyond survival, our capacity to care about things larger than ourselves. The dreamers follow that need wherever it leads. The personal stories often include sacrifices that aren't purely professional. Time away from family, relationships strained by travel and odd hours, financial uncertainty early in careers, geographic mobility required to follow opportunities, children growing up visiting observatories as playgrounds, partners adapting to the rhythms of research, the cycles of proposal deadlines, and observing runs. The human element extends beyond the dreamer to encompass everyone who supports them, who makes it possible for them to pursue their work. Yet many also speak of richness their work brings to life, the privilege of thinking deeply about fundamental questions, the beauty of the images they work with, the satisfaction of contributing, even in small ways, to humanity's collective understanding. The friendships formed with fellow dreamers who share the same passion. The moments of breakthrough when a puzzle finally makes sense. The work gives meaning, purpose, connection to something vast and enduring. Teaching the next generation is part of the dreamer's role, passing on not just knowledge but enthusiasm, not just techniques but values. Showing students that it's okay to pursue questions that have no immediate application, that curiosity is valuable for its own sake. Mentoring young researchers, helping them navigate the challenges, encouraging them when results don't come easily. The dreamers reproduce themselves not biologically but intellectually, each generation teaching the next, creating a lineage of inquiry that stretches across centuries. The human element also includes the broader public, the people who never become professional astronomers, but who care about the questions. They attend public lectures, read popular books, visit planetariums, follow news of new discoveries. Their support, their interest, their sense that counting galaxies matters, sustains the enterprise. Tax dollars fund telescopes. Private donors contribute to research. Politicians approve budgets. All because enough people value the pursuit, understand that exploring the universe expands human horizons in ways that benefit everyone, even if the benefits are hard to quantify. When you see an image of thousands of galaxies, remember that each one was detected by someone, measured by someone, studied by someone. Behind the technical achievement lies human effort, human curiosity, human dedication. The galaxies exist whether we count them or not, but the counting happens because dreamers chose to do it. They could have done something else with their lives. They chose this, and because they did, we know more about the universe than any previous generation. We have better maps, more accurate counts, deeper understanding. That knowledge is a gift from the dreamers to all of us, a testament to what humans can achieve when we turn our gaze outward and ask how much is there? How far does it go? How many wonders remain to be found? The pursuit of truth is rarely smooth. For every discovery, there's skepticism. For every new measurement, there's debate about its accuracy. The quest to count galaxies has faced opposition at every stage, not from ignorance or hostility, but from the natural caution of science, the requirement that claims be supported by evidence, that conclusions withstand scrutiny. This opposition, properly channeled, strengthens rather than weakens the search for truth. The first opposition came from technical limitations. Early telescopes simply couldn't see faint enough to detect most galaxies. The brightest ones, the nearest, those were observable. But the vast majority remained invisible, hidden by the dual barriers of distance and dimness. Critics of higher galaxy counts could legitimately argue that extrapolations from visible galaxies to the total population involved too many assumptions. Maybe bright galaxies were rare. Maybe faint ones didn't exist in the numbers theorists predicted. Without direct detection, how could anyone be certain? This opposition forced astronomers to push technology forward. Each generation of instruments had to prove itself, had to demonstrate that it could detect fainter objects reliably, that its measurements were calibrated correctly, that artifacts and noise didn't masquerade as galaxies. The burden of proof lay with those claiming higher counts. They had to show their data, share their methods, allow independent verification. The opposition demanded rigor, and the science became stronger for it. There was also opposition from theoretical quarters. Some models of the universe predicted lower galaxy counts than observations suggested. When measurements exceeded predictions, theorists had to decide whether their models were wrong or the observations uncertain. Often, initial reaction leaned toward questioning the observations. Perhaps the detections were spurious. Perhaps the statistical methods flawed. Perhaps systematic errors inflated the count. These questions weren't attacks, but necessary checks, ways to ensure that conclusions rested on solid foundations. The opposition between different observational groups sometimes grew heated. When one team published a galaxy count, others would scrutinize the methodology, looking for weaknesses. Did they account for contamination from stars? Did their completeness corrections make sense? Were their distance estimates reliable? This adversarial peer review could be uncomfortable for those whose work was being challenged, but it served a vital function. It filtered out errors, reinforced best practices, built consensus around results that survived scrutiny. Funding battles represented another form of opposition. Not everyone agreed that counting galaxies deserved significant resources. Telescope time, research grants, satellite missions all competed for limited funds. Advocates for galaxy surveys had to make their case, arguing that understanding the large-scale structure of the universe justified the expense. Critics countered with other priorities, equally valid, equally important. The competition for resources forced clear articulation of why galaxy counts mattered, what questions they addressed, what benefits they provided. Opposition also came from the public and media when results seemed too strange or counterintuitive. 2 trillion galaxies. How could anyone possibly count that many? Wasn't the number just made up? These questions reflected healthy skepticism, a demand for explanation that forced astronomers to communicate better, to show how extrapolation worked, to demonstrate that the methods were sound even if the numbers were staggering. The need to explain to non-experts improved scientific communication and built public trust. Philosophical opposition questioned whether counting galaxies was even meaningful. If the universe might be infinite, does the count in the observable portion matter? If we can never verify the total, is the exercise futile? These challenges came not from hostility, but from serious thinkers wrestling with the implications. They forced astronomers to clarify what they meant by counting, what assumptions undergirded their claims, what limitations bounded their knowledge. The opposition sharpened thinking, made arguments more precise. Technical opposition around detection thresholds has been persistent. At what point does a faint smudge in an image count as a galaxy rather than noise? Where's the line? Different researchers use different criteria, leading to different counts from the same data. The opposition here was methodological. Debates about how to set thresholds, how to estimate completeness, how to correct for selection effects. These debates continue, reflecting genuine uncertainty about how to define and detect the faintest galaxies. There was opposition to the very definition of a galaxy. Is a small cluster of stars orbiting a larger galaxy a separate entity or a satellite? When two galaxies merge, at what point do they become one? The opposition forced development of clear taxonomies, quantitative criteria for what counts as a galaxy. The resulting definitions aren't perfect, but they're transparent and consistent, allowing meaningful comparisons across different surveys. Replication provided a form of opposition. When one team reported a result, others tried to reproduce it. Sometimes they succeeded, confirming the finding. Sometimes they failed, suggesting the original result was wrong or needed refinement. This opposition through replication is fundamental to science. It builds confidence when results hold up, identifies problems when they don't. The quest to count galaxies advanced through countless cycles of claim and verification, each test strengthening the consensus or revealing errors that needed correction. Opposition from unexpected observations forced revisions. When the James Webb Space Telescope found brighter, more massive galaxies in the early universe than expected, it challenged existing galaxy formation models. The opposition wasn't to the observations themselves, but to what they implied. If early galaxies were more numerous or larger than predicted, the count might need adjustment. This opposition between observation and theory drives progress, forcing both to improve until they align. Cultural opposition occasionally appeared when galaxy counts seemed to diminish human significance. If there are trillions of galaxies, what does that make us? This existential opposition came from those uncomfortable with cosmic scales, with implications that might threaten certain worldviews. Astronomers responded not by changing their findings, but by contextualizing them, showing that vastness doesn't negate meaning, that understanding our small place can be enriching rather than diminishing. The opposition of complexity has been constant. The universe refuses to be simple. Galaxies come in too many types, at too many distances, in too many environments. Models that work for one population fail for another. Extrapolations that seem reasonable prove inaccurate. The complexity itself opposes easy answers, forces more sophisticated approaches, demands ever more careful analysis. This isn't opposition from people, but from nature, from the irreducible intricacy of reality. Budget cuts represented opposition through constraint. When funding decreased, surveys slowed or stopped. Telescopes went unbuilt. Researchers left the field. This opposition wasn't intentional, but it affected progress as surely as any scientific debate. The battle for truth required not just good ideas, but sustained support, and that support sometimes wavered as priorities shifted. Advocates for galaxy surveys had to continually make the case, justify the expense, demonstrate the value. Skepticism about extrapolation methods was justified opposition. How do you know that a small sample represents the whole? What if the patches you observed were unusual? What if faint galaxies clustered differently than bright ones? These questions demanded statistical sophistication, careful uncertainty estimates, tests to verify that samples were representative. The opposition pushed development of better sampling strategies, more robust statistical methods, more honest assessments of uncertainty. The opposition throughout this quest hasn't been obstacle so much as refining fire. It burned away weak arguments, poor data, hasty conclusions. What remained was stronger, more reliable, more trustworthy. The galaxy counts we have today survived opposition from every direction: technical, theoretical, methodological, philosophical. They stand not because everyone agreed from the start, but because they withstood challenge after challenge, emerging validated through rigorous testing. This is how science works at its best. Opposition isn't the enemy of truth, but its partner. Through conflict, through challenge, through the demand for evidence and the rejection of unsupported claims, we approach reality more closely. The battle for truth about how many galaxies exist continues, with new observations prompting new debates, new techniques enabling new tests. The opposition never stops, and that's exactly as it should be. Truth isn't given, it's earned through persistent inquiry, rigorous testing, and the willingness to face opposition with better evidence, clearer arguments, and endless patience. There comes a moment, not sudden but gradual, when understanding shifts into something deeper. It's not just knowing a fact but feeling its weight, sensing its implications, allowing it to change how you see everything. For humanity's relationship with galaxies, that awakening has been unfolding slowly, a collective realization that we inhabit a universe far more populated, more ancient, and more wondrous than our ancestors could have conceived. The awakening begins with scale. 2 trillion galaxies. The number is so large it initially means nothing. It's just a figure, abstract, disconnected from experience. But sit with it. Let it unfold. 2 trillion means that if you counted 1 galaxy per second, never stopping to sleep or eat, it would take you over 60,000 years to count them all. It means that the number of galaxies exceeds the number of people who have ever lived. It means that if you assigned every person on Earth their own collection of galaxies, each would receive about 250 of them. The scale becomes personal when you realize that each of those trillion-plus galaxies contains typically hundreds of billions of stars. Multiply those numbers, and you arrive at more stars in the observable universe than grains of sand on all Earth's beaches. More stars than seconds have passed since humans first looked up and wondered. The numbers stop being abstract and start becoming visceral, a weight pressing on consciousness, demanding acknowledgement. But the awakening isn't just about big numbers. It's about what those numbers represent. Each galaxy is a place, a structure where physics plays out over billions of years, where stars are born and die, where elements form and scatter, where, perhaps, life emerges and wonders at its own existence. The 2 trillion aren't just objects. They're opportunities, possibilities, experiments in how matter organizes when given space and time. The temporal aspect deepens the awakening. The light we see from distant galaxies left them billions of years ago. We're not seeing the universe as it is, but as it was. The farthest galaxies visible to the James Webb Space Telescope appear as they existed only a few 100 million years after the Big Bang. They're snapshots from cosmic infancy. Those galaxies, if they still exist, have evolved unrecognizably. They might have merged with neighbors, grown enormously, or been torn apart by gravitational interactions. We see their youth, but we'll never see their present. The awakening includes accepting that vast cosmic now is invisible to us, hidden behind the speed of light. This awareness of deep time changes perspective. The galaxies remind us that the universe has a history, that everything we see is temporary, that even structures as massive as galaxies are not eternal. They form, evolve, and eventually will fade. Our own Milky Way will merge with Andromeda in a few billion years, creating a new galaxy that bears little resemblance to either parent. The awakening to cosmic time makes human timescales seem fleeting, our civilizations momentary, our individual lives briefer than a single heartbeat in the universe's slow rhythm. Yet the awakening doesn't diminish us. It places us within context. We exist because galaxies exist. The atoms in our bodies were forged in stars that lived and died in galaxies that formed billions of years ago. We're not separate from the galaxy count. We're part of it. The Milky Way is one of those trillion plus, and we're woven into its fabric, made of its matter, sustained by its oldest star, the Sun. The awakening includes recognizing that we're not outside the universe looking in. We're inside it, participants in its unfolding story. The philosophical awakening involves confronting cosmic loneliness and connection simultaneously. With trillions of galaxies, surely we're not alone. Surely life has emerged elsewhere. Intelligence developed. Civilizations wondered at their own night skies. The numbers suggest abundance, that the universe is probably teeming with life at various stages of development. Yet the distances are so vast that we might never know for certain. Light takes millions or billions of years to travel between galaxies. Even within our own galaxy, distances are measured in thousands of light years. We might be cosmically surrounded by company, and yet practically isolated, unable to ever meet our neighbors. This paradox, connection through isolation, is part of the awakening. We're not unique, but we're alone with our non-uniqueness. The realization is both humbling and strangely comforting. Humbling because it shows we're not special. Comforting because it suggests the universe is creative, that wherever conditions allow, complexity emerges, consciousness develops, wonder arises. We're one instance of a pattern that likely repeats throughout those trillions of galaxies. The awakening also includes accepting uncertainty as permanent. We'll never know the exact number of galaxies. The count will always be an estimate, subject to revision as instruments improve and methods refine. The universe doesn't owe us completeness. It presents itself partially through the limited window of electromagnetic radiation across the constrained span of cosmic time we can access. The awakening means embracing that our knowledge is fragmentary, that mystery persists no matter how much we learn. There's an aesthetic awakening too. Deep field images aren't just scientific data. They're beautiful, strangely moving. They're random scatter of colored shapes creating patterns that feel meaningful even if they're not designed. The beauty of galaxies operates on multiple levels. The immediate visual appeal and the deeper beauty of knowing what you're looking at, understanding that each smudge represents billions of stars, that the image captures light from across cosmic history. The awakening includes developing an eye for this layered beauty, learning to see not just shapes but significance. The ethical dimension of the awakening is subtle. If the universe contains trillions of galaxies, possibly countless living worlds, what are our responsibilities? Do we have obligations to protect Earth's biosphere, not just for our sake, but as one of the universe's experiments in complexity? Does cosmic abundance make Earth less precious, or more, as the only planet we can actually protect? The awakening doesn't provide answers, but poses questions that didn't exist before we knew the scale of cosmic structure. The spiritual awakening, for those inclined that way, involves redefining the sacred. If creation encompasses trillions of galaxies, then whatever creative principle lies behind existence operates on a scale that dwarfs any human conception of divinity. The universe becomes either evidence of something beyond itself, or it becomes self-sufficient, requiring no explanation beyond its own existence. The awakening forces engagement with ultimate questions about origins and purposes, about whether meaning exists inherently or must be created. For many, the awakening is ongoing, never complete. Each new image from space telescopes, each refined galaxy count, each discovery of galaxies in unexpected places or times deepens the awareness. The learning never stops because the universe keeps revealing new layers. What seemed comprehended becomes strange again. Certainties dissolve. Questions multiply. The awakening is not a destination but a process, a continuous expansion of consciousness to accommodate expanding knowledge. The collective awakening of humanity to galactic abundance is still unfolding. Most people don't think about galaxy counts daily, but the knowledge is there, part of the cultural background, occasionally surfacing in conversations or contemplations. When someone looks up at the night sky now, even if they don't consciously recall the numbers, the awareness exists somewhere that what they see is a tiny fraction of what exists, that the darkness hides vastness beyond imagination. That background awareness shapes how we think about our place, our importance, our relationship to the cosmos. The awakening ultimately is about proportion, understanding that we're small but not nothing, that we're temporary but not meaningless, that we're one among trillions of possibilities but still unique in our particular expression. The galaxies, in their overwhelming numbers and stunning distances, provide the scale against which we measure ourselves. They show us what vastness looks like, and in doing so, they show us what we are. Finite beings capable of grasping infinity, mortal consciousness touching the eternal, tiny but aware, small but awake. After all the counting, all the observations, all the analysis and debate, a deeper truth emerges, one that transcends the numbers themselves. The question of how many galaxies exist in the universe is really a question about existence itself, about the nature of reality, about what it means that anything is here at all. The revelation isn't just quantitative, it's qualitative, philosophical, almost mystical in its implications. The deepest truth is that the universe is profoundly generous. It didn't create one galaxy and stop. It didn't make a few and call that sufficient. It made trillions, each one unique, each one a separate experiment in how matter and energy organize over cosmic time. This abundance isn't random. It flows from the laws of physics, from the initial conditions after the Big Bang, from the way gravity and expansion balance against each other. But the result is overwhelming richness, a cosmos that fills every available space with structure and light. That generosity extends to every scale. Within each galaxy, billions of stars. Around many stars, planets. On at least one planet, life. Within life, consciousness. Within consciousness, the ability to wonder about galaxies. The universe creates abundantly at every level, from particles to galaxies, from atoms to awareness. The revelation is that creativity seems fundamental to existence, that the cosmos is not static but endlessly productive, constantly bringing new forms into being. The revelation also includes recognition of unity. Despite their enormous numbers and vast separations, all galaxies follow the same physics. The laws that govern gravity, electromagnetism, and nuclear forces operate identically everywhere. A hydrogen atom in a galaxy 13 billion light-years away behaves exactly like one in a laboratory on Earth. The universe is not a collection of separate things obeying different rules. It's a single system, unified by consistent principles, connected through space and time by the same fundamental reality. This unity means that studying any part reveals the whole. Understanding how one galaxy forms tells us about galaxy formation generally. Measuring expansion here tells us about expansion everywhere. The revelation is that local knowledge has cosmic significance, that we don't need to visit every galaxy to understand them. The universe repeats itself. Not exactly, but thematically, the same patterns playing out in different contexts. We belong to that repetition, our existence following patterns that likely appear throughout the cosmos. The revelation includes accepting that most of what exists is invisible. Dark matter outweighs visible matter by about 5 to 1. Dark energy dominates even more strongly, making up about 70% of the universe's content. The galaxies we count, magnificent as they are, represent only a fraction of reality. The deepest truth is that the universe is mostly hidden, that what we see, as abundant as it appears, is only the luminous tip of something much larger. We live surrounded by the invisible, shaped by forces we can't directly detect, participating in structures we can only infer. This revelation about invisibility extends to limits of knowledge. We'll never see beyond the cosmic horizon. We'll never know if the universe is infinite or finite in extent. We'll never count every galaxy or catalogue every star. The universe, maintains its mystery, preserving uncertainty no matter how much we learn. The deepest truth is that reality exceeds comprehension, that finitude can never fully grasp infinity, that the questions will always outnumber the answers. Yet within those limits, knowledge is possible. We can count galaxies in the observable universe. We can measure their properties, trace their evolution, understand their structure. The revelation is that partial knowledge is still knowledge, that we don't need omniscience to achieve understanding. The universe reveals itself proportional to our ability to look and comprehend. It meets us where we are, accessible to inquiry even if never fully knowable. The temporal revelation is profound. The universe has a history, a developmental arc from simple to complex, from smooth to structured, from hot to cool. The galaxies we see today didn't exist in the earliest moments after the Big Bang. They formed over billions of years as matter coalesced under gravity's patient pull. Time isn't just a dimension through which things move. It's a creative force, the medium in which possibility becomes actuality. The revelation is that the universe is still unfolding, still creating, still changing. We observe not a finished product, but a work in progress. This developmental perspective transforms how we think about counting. The number of galaxies isn't constant across time. In the early universe, there were more smaller galaxies. Through mergers and collisions, the count has decreased while average size increased. In the far future, as expansion accelerates, galaxies will become increasingly isolated, their light red-shifted beyond detection. The count changes depending on when you ask. The revelation is that the universe is dynamic, that static numbers can't capture its evolving nature. The revelation about meaning is perhaps most personal. In a universe of trillions of galaxies, what does any individual galaxy matter? What does any individual star matter? What does any individual life matter? The answer the revelation offers is paradoxical. Nothing matters more than anything else, and everything matters completely. There's no cosmic hierarchy of importance. A galaxy isn't more significant than a person, nor a person less significant than a galaxy. Each is an expression of existence, a way the universe realizes possibility. Mattering isn't about scale. It's about being. This democratic view of significance means we don't need to be central to matter. The Copernican principle, the idea that we occupy no special place, isn't diminishing. It's liberating. We matter because we exist, because we're part of the pattern, because we contribute to the universe's diversity. Our importance doesn't depend on being unique. It comes from participation, from being one of the countless ways existence manifests. The revelation is that in a universe of abundance, there's room for everyone and everything to matter. The revelation about connection is equally important. Despite vast distances, everything is linked. The atoms in your body come from stars that died billions of years ago. The light entering your eyes right now began its journey from distant galaxies in the deep past. You exist within gravitational fields that extend across cosmic distances, weak but real. Your awareness of galaxies creates a connection across space and time, joining your moment to theirs. The revelation is that isolation is illusion. We're woven into the cosmic fabric, inseparable from the whole. The ethical revelation flows from this connection. If we're part of the universe, then how we treat our local environment matters cosmically. Not because Earth is special, but because it's representative. One example of the universe organizing into complexity and awareness. To destroy that complexity, to end that awareness, would be to diminish the cosmic pattern. The revelation suggests responsibility, not imposed from outside but inherent in our relationship to existence. We care for Earth because it's part of the universe, caring for itself through us. The revelation about limits is strangely freeing. We can't visit other galaxies. We can't even visit most stars in our own galaxy. The distances are too vast, the timescales too long. But that limitation forces appreciation of what we can reach. Earth becomes precious not because it's all there is, but because it's all we can touch. The local becomes valuable precisely because the cosmic is inaccessible. The revelation is that limits create value, that infinity without boundary would be meaningless, that finitude gives weight to existence. The final revelation is about process. Counting galaxies isn't about reaching a number. It's about engaging with vastness, about pushing the boundaries of what can be known, about participating in the universe's self-awareness. Each observation, each measurement, each moment of understanding is the universe examining itself through human consciousness. We're not separate observers. We're the mechanism by which reality becomes known to itself. The revelation is that awareness isn't incidental to the cosmos. It's integral, part of how existence unfolds. The deepest truth, then, is that the question of how many galaxies exist is less important than the act of asking. The number matters, yes, for what it reveals about cosmic structure and evolution, but the asking matters more because it represents consciousness engaging with existence, finitude touching infinity, the temporary contemplating the eternal. The galaxies, in their trillions, become mirrors in which the universe sees itself, and we, briefly aware, serve as those reflective surfaces. That's the revelation, the deepest truth, the meaning beneath the numbers. Existence aware of itself, awareness embedded in existence, the counter and the counted unified in the act of counting. The numbers have been presented, the evidence examined, the story told. But what does to it all mean? When you know that trillions of galaxies fill the observable universe, each containing billions of stars, each separated by distances that light takes millions of years to cross, what do you do with that knowledge? How does it change you? What does it ask of you? Perhaps the first response is simply to sit with the scale, not to rush toward interpretation or significance, but to let the vastness wash over you. 2 trillion galaxies. Try to picture that. Try to hold it in your mind. You can't, of course. The number is too large for human consciousness to grasp in its entirety. But the attempt itself is valuable. It stretches the mind, opens it to scales beyond the everyday, reminds you that reality extends far beyond immediate perception. Some people feel small when contemplating cosmic scale. The universe is so vast, galaxies so numerous, that individual existence seems to shrink to insignificance. A single person on a single planet in a single solar system in one galaxy among trillions, what weight could that possibly carry? This feeling of smallness isn't wrong. It's accurate recognition of proportion. We are small, measured against galaxies. Our lives brief, measured against cosmic time. Our influence limited, measured against universal scales. But smallness doesn't mean meaninglessness. A single atom is small compared to a person, yet without atoms there are no people. Small things compose large things at every scale. You're small in a universe of galaxies, but you're also the scale at which awareness happens, where understanding emerges, where meaning is created. The universe can be vast, and you can be small, and both can matter completely. Scale doesn't determine significance, being does. Others feel connected rather than diminished. The realization that we're made of stardust, that our atoms were forged in stellar furnaces in some galaxy long ago, creates a sense of belonging. We're not separate from the cosmos. We're continuous with it, woven into its fabric at the most fundamental level. The galaxies aren't out there, distant and alien. They're us, or we're them. Different expressions of the same matter and energy following the same laws. This perspective doesn't deny smallness but contextualizes it. Yes, we're small, but we're small parts of something magnificent. The temporal dimension adds another layer to reflection. The light we see from distant galaxies is ancient, older than our species, older than our planet. When you look at a galaxy 10 billion light years away, you're seeing it as it existed before the solar system formed. That galaxy's now, its present moment, is invisible to you. Hidden behind the speed of light, you see only its past. The reflection here is that time itself is strange, that simultaneity doesn't exist across cosmic distances, that the present is local and the past is what we share with the distant universe. This makes looking at the night sky a form of time travel. You're not seeing the universe as it is, but as it was, a collage of different eras layered on top of each other. The nearest stars appear as they were years ago, distant galaxies as they were billions of years ago. The sky is a museum of light, each photon a messenger from some moment in cosmic history. The reflection might lead you to appreciate transience, the way everything flows and changes, how the permanent is always temporary and the eternal is always now. The mystery remains despite all we've learned. We can count galaxies, but we can't explain why there's anything to count. Why does the universe exist at all? Why these laws of physics rather than others? Why did the Big Bang happen? The deepest questions remain unanswered, possibly unanswerable. The reflection here might be acceptance, the recognition that knowledge has limits, that some mysteries might be intrinsic rather than solvable. We live within the question, not beyond it. Yet that mystery doesn't invalidate what we've discovered. We might not know why the universe exists, but we know a great deal about how it works. We can trace its evolution from the Big Bang to now. We can map its structure across billions of light years. We can predict its future evolution. The reflection is that partial knowledge is still valuable, that understanding how doesn't require knowing why, that the universe can be comprehensible without being completely explained. The ethical reflection asks what obligations come with knowledge. If we know the universe contains trillions of galaxies, probably countless living worlds, does that change how we should behave? Does it make local concerns seem trivial, or does it make them more urgent? One view says, nothing we do matters on cosmic scales. The universe is too vast to notice or care about human affairs. Another view says everything we do matters because it happens, because it's real, because effects are real regardless of scale. The reflection doesn't resolve this tension but holds it, acknowledging both the cosmic indifference and the local significance. There's also aesthetic reflection. The images of galaxies are beautiful, not just scientifically interesting but visually compelling. That beauty seems gratuitous. The universe didn't need to be beautiful for galaxies to function, yet they are. Spirals curving with mathematical elegance, ellipticals glowing with soft gradients, collisions creating dramatic streamers and shells. The reflection might be that beauty emerges naturally from physical laws, that pattern and form are intrinsic to matter organizing itself, that aesthetics isn't separate from physics but a natural consequence of it. The personal reflection asks how the knowledge changes you. Does knowing about trillions of galaxies alter your daily life? Probably not directly. You still need to eat, work, relate to others, handle the demands of existence. But it might shift perspective subtly. Problems that seemed overwhelming might feel smaller. Anxieties that dominated consciousness might recede slightly. Not because they don't matter, but because they're placed in context. You still experience them fully, but you might also carry an awareness that they're local, temporary, one small fluctuation in a universe that continues regardless. The universe will outlast all our troubles. Long after humanity is gone, the galaxies will still be shining, still following their orbits, still evolving on their slow timescales. There's peace in knowing that the cosmic story continues beyond our chapter. Others find it disturbing. The thought that nothing we do echoes into deep time, that the universe remembers nothing. The reflection accommodates both responses, the comfort and the disturbance, without choosing between them. The spiritual reflection, for those inclined toward it, wonders about purpose. If the universe made trillions of galaxies, was that intentional? Is there design? Or only process? Different. Traditions offer different answers. Some see the abundance as evidence of a creative intelligence, others as the natural result of physical laws operating over time. The reflection here isn't about settling the question but exploring it, considering what it would mean either way, how it affects understanding of existence and meaning. The social reflection considers how shared knowledge of galactic abundance affects human culture. We all live under the same sky. We all inherit the same cosmic context. Does that create bonds? Does awareness of the vast universe make human distinctions seem smaller, less important? Can cosmic perspective foster humility, cooperation, peace? History suggests knowledge alone doesn't change behavior much. People have known Earth is round for centuries but still maintain parochial views. Yet maybe cumulative awareness builds slowly, that each generation raised with knowledge of trillions of galaxies absorbs it more deeply, lets it shape worldview more. Fundamentally, the reflection ultimately leads back to wonder. After all the analysis, all the numbers, all the interpretation, what remains is the sheer astonishment that any of this exists, that there are galaxies at all, that we can see them, that we can count them, that we can wonder about them. The universe didn't have to be this way. It didn't have to produce awareness that could contemplate its own existence. Yet it did, and here we are, briefly conscious, looking out at trillions of galaxies, trying to understand what it means. The reflection ends where it began, in wonder, but now informed by knowledge, deepened by understanding, enriched by contemplation. The question that opened this journey, how many galaxies are in our universe, has been explored from every angle. We've traced its history from the first discovery that other galaxies exist to the modern estimates that count them in the trillions. We've examined the methods, the challenges, the people, and the implications. But now, as this story draws toward its close, the question remains open, as it always will, because the universe itself remains open, still unfolding, still revealing, still inviting wonder. The legacy of counting galaxies isn't a final number, it's a way of seeing. Once you know that the universe contains trillions of galaxies, you can never look at the night sky the same way. The darkness becomes populated, the silence becomes full, the emptiness becomes abundance. This shift in perspective is the true legacy, passed from generation to generation, expanding with each new discovery, deepening with each refined measurement. We leave to future generations not just data but a transformed relationship with the cosmos. The count will continue. New telescopes will see farther, detect fainter galaxies, push the boundary of observation deeper into space and time. Each improvement will add to the total, refining estimates, adjusting models, sometimes surprising us with the unexpected. The James Webb Space Telescope has already begun this process, finding galaxies brighter and more massive than predictions suggested. Future instruments will do the same, each pushing the envelope, each revealing that the universe still has secrets to share. The legacy is not completion, but continuation. The methods developed for counting galaxies have spread beyond astronomy. Image processing algorithms, statistical techniques for handling large data sets, machine learning approaches for classification, all these tools forged in the pursuit of galaxies now serve other fields. Medical imaging uses similar methods to detect subtle features in scans. Earth observation satellites process images with techniques pioneered for deep fields. The legacy extends into unexpected domains, touching lives far removed from telescopes and cosmic surveys. The human legacy matters too. The astronomers who devoted careers to counting galaxies leave behind not just papers and data, but inspiration. They showed that humans can pursue knowledge for its own sake, can work toward understanding even when the questions have no practical application. They demonstrated patience, persistence, and passion. Their legacy lives in students they mentored, in collaborators they worked with, in anyone who looked at their work and felt called to contribute to the collective human project of understanding the universe. The philosophical legacy is perhaps most enduring. The abundance of galaxies changed how we think about existence, about significance, about meaning. It forced confrontation with scales that dwarf human concerns, while also revealing that we're part of the pattern, made of the same matter, following the same laws. This dual awareness of smallness and connection, of insignificance and belonging, is part of the legacy. It shapes how we approach other questions, how we think about our place, how we navigate the tension between the cosmic and the personal. The aesthetic. Legacy appears in art and culture. Images of galaxies have become iconic, appearing in contexts far beyond scientific publications. They inspire paintings, sculptures, music, poetry. The spiral shape of galaxies echoes through design. The deep field's random scatter of light becomes a motif for abundance and possibility. Artists draw on the imagery, and through their work, the legacy reaches people who never study astronomy, but whose lives are nevertheless touched by the beauty and mystery of cosmic structure. The educational legacy grows with each generation. Children today grow up seeing images of thousands of galaxies in textbooks and museums. They absorb from early ages that the universe is vast, old, and filled with structure. This knowledge becomes foundational, shaping how they think about everything else. The legacy is normalized wonder, cosmic perspective embedded in basic education, the understanding that we inhabit one small corner of an incomprehensibly large universe. But the journey must return to where it began, to you, lying in the darkness, listening to these words, breathing slowly as the day's concerns fade and sleep approaches. The galaxies counted in this story are still out there, still shining, still separated by vast distances, still following their ancient orbits. You can't see most of them. Your eyes detect only the nearest stars, all belonging to the Milky Way. But knowing they exist changes the darkness. It fills it with hidden light, with structures too faint to see but too real to ignore. The return is to the immediate, to the present moment, to this breath and the next. The cosmic scale recedes. The trillions of galaxies fade from active thought. What remains is the quiet, the stillness, the gentle awareness that you exist within something vast and wonderful. The knowledge doesn't burden, it supports. It provides context without demanding attention. It's there when you want it, receding when you don't. A background awareness that the universe is larger than troubles, older than anxieties, richer than fears. The legacy we each carry is our own encounter with the question. Whether you remembered the number, forgot it, or never focused on it precisely doesn't matter. What matters is the engagement, the moment of considering how many galaxies might exist, of trying to wrap your mind around cosmic scales, of feeling something shift as understanding deepens. That personal legacy, your own private relationship with the question, is part of the larger story. You counted yourself among those who wondered, and that counts for something. The closing isn't an ending. The story of counting galaxies continues without you and me, carried forward by astronomers who right now are analyzing data, planning observations, building instruments for future surveys. The work goes on because the questions remain alive, because curiosity persists, because the universe keeps offering more to discover. We're drops in that stream, here, briefly, contributing what we can, then passing the work to others. The legacy is the stream itself, not any individual contribution to it. So as you drift towards sleep, let the galaxies drift too. They don't need your attention to exist. They'll be there tomorrow, still shining, still numerous beyond counting, still waiting for anyone who wants to look. The night sky above you, whether you can see it or not, is the same sky that covers everyone, everywhere, always. The same photons fall on all of us. The same cosmic story contains all our smaller stories. Under the same endless sky, we're connected, not just to each other but to everything, to the stars that made our atoms, to the galaxies that fill space, to the universe that brought all of this into being and sustains it still. The legacy of counting galaxies is the reminder of that connection, the knowledge that we belong to something vast, that we're part of a pattern that includes trillions of galaxies and also includes you, here, now, breathing softly, ready to rest. The question of how many galaxies exist doesn't have a final answer, but it has an invitation to look up, to wonder, to count what can be counted and accept what cannot, to find your place within the vastness, neither lost nor central, but present, aware, briefly conscious. That's the legacy. That's the return. That's the gift of counting galaxies, the knowledge that enriches without overwhelming, that expands without diminishing, that reminds us we live in a universe generous beyond measure. So rest now. The galaxies will keep turning, the universe will keep expanding, and you, carried on a small planet through the vast night, will keep being exactly what you are, a witness to it all, a moment of awareness in the cosmic story, connected to everything through the simple fact of existing. The count continues, the mystery endures, and under the same endless sky, we all find our place in the light.